Yeah. Hello and welcome back to Coding for Unreal Engine in C++. Welcome to episode 7 of this ongoing tutorials series here on the Devcom channel. And last week we started climbing down one of the deepest rabbit holes that C or C++ for that matter have to offer for us. We started to climb down the rabbit hole of pointers, and we didn't actually reach the bottom of it. There's quite some way to go, and this is what we're going to be doing today. We'll be continuing our talk about pointers and see how deep the rabbit hole goes, and if we can maybe make at least some sense to the weirdness that C pointers are. Let's get started. Yes, and here we are again. Welcome to, I hope for you a wonderful evening. I hope you had a wonderful day, or if you're looking the recording of this, a wonderful whatever you had before you started watching the video. Maybe an amazing lunch, you met an old friend, and you had the best lunch for the whole year, and now you're completely up to the challenge to see, okay, what... excuse me. What has C more for me to offer in terms of total confusion and all those things? You can already see it down there. I already pulled out my amazing paint skills. This time I'm not sure if you can already see it in the little preview down there, but in a few moments I'll be switching over to the other view where you can actually see stuff way more better. This time I actually used the line drawing tool to make those neat little rectangles, because at first we will be going over of what we did and what we looked at last time, because if you just watched the previous video and you're now immediately watching this one, you might like, hey, I just watched the other one, but what gives? I mean, just please do continue. But in real time, if you're watching this directly on Twitch, there's a week since the last time, and this is a very, very confusing and very complex topic. So I think summarizing all the things, even if you watch these videos back to back and you exactly know what we kind of just talked about, just summarizing in short what we talked about the last time, and then picking up and continuing on what more stuff there is, I think is quite a good idea. Just as it, even if you just watched it, so just to summarize it again, these were the things we have so far. And now we're building up on this, because one thing we're going to be doing is this goes with, we have done this a few times already in the past, especially when we made the game of Go, the game of life. Yeah, there's a game of Go, which is also quite nice. There's a game of Go, there's a language of Go, and there's a game of life. But there's not a language of life. Is there a language of life? I don't know. So we did this when we did the Game of Life implementation. You remember we spawned all these actors and we saved references to these actors in a local map, so we could access them and do stuff with them, or know which one was clicked, or trigger functions on them. So these references that we stored to these actors were in essence, they were pointers. These references basically just were a simple pointer to wherever that actor is stored in memory, or the object that then comprises the actor. And this is exactly what we're going to today. We're not doing we're not spawning an actor and getting this, because that thing's way too huge. We're building a very, very simple own class, basically a completely empty class, and maybe two. Let's see, depending on how much stuff we want to try out. And we'll just be putting a simple method in that just prints something into the log and says, yeah, here I am. I've been called, I've been accessed or something. And then we will take a look at this reference we're getting back, because when we create an object, if you spawn an actor, it's very much the same as creating a new object based on one of your classes you've defined, because spawning an actor actually, well, what happens under the hood is the engine then instantiates the class that defines your actor, that defines everything your actor is and can do, and the properties it has. And part of the properties, there's a whole lot of more magic behind the scenes going on, because there's lots and lots of code the engine already supplies for an actor. This is why we inherit from the actor class. There's lots and lots of stuff. And some of this stuff is to see, do you have any references to any components that need to be displayed on the scene, which makes our actor then actually be visible. That's all stuff we don't need today. But basically, it's just in a class that gets instantiated into an object, and then a lot of code runs to process all the properties it has. This is why we're using game engines, because there's quite a lot of stuff going on in the background that we don't have to care about. It's just been done for us, and we just have to use it, which is quite nice. So we'll be one of the things we'll be doing today is creating an on class, just a simple empty class, putting something in there, instantiating at it, looking at the reference, the pointer we're getting back, and see what silly things we can do with that pointer. Last week we tried to crash the engine and we were successful. We completely crushed that thing down with I don't know, coming up with pointers that basically didn't exist. We had a valid pointer to a value, and then we just added a bunch of numbers to it, and it ended up in completely invalid memory space. So, and also there's one thing I unfortunately haven't found out yet. I can, spoiler alert, I can not answer this question right away, because when we're printing out the pointers, because what we did, and again in doing summarizing what all we did, we will be doing this again. We printed out the actual pointers, where in memory everything is. And yeah, it was kind of weird. We always had this B9 prefix in front of it, and stuff was quite confusing, because that's how pointers are. They are just confusing. And I did not find out what the B9 prefix is for. I found something that might have to do with it, but I wouldn't know why we get this as a prefix when we're just trying to access the pointer location, because B9 is actually the CPU command, the binary CPU command to load an address into a special register that's then used to access this memory location. And we're talking, because it means since I'm doing this all on my PC, we're talking, of course, x86 platform. And the B9 is actually a binary, and there's two. There's B8 and there's B9, I think. And those are actually the binary commands the CPU executes to then load. And actually the x86, so your Intel or your AMD CPU, they have other CPUs like the ARM chips in your mobile phone. They might have different command sets. Their binary representation of things to do does look different, because they are completely different architectures. But especially on CPUs we have in our PCs, there is the B9 is actually the command to load this address into the register that's then used to read the contents of memory stored in that register. This sounds like this could be the reason why we're getting the B9 prefix for our pointer. Like, yeah, you're getting something back that you can immediately slap at the CPU. You don't have to do anything with just give this whole thing the CPU, and the CPU already then can directly execute this. This sounds like it would make sense, but I am not sure. I did nowhere did I find a documentation or a specification when you're getting a pointer in C++ on modern systems with modern compilers, why you're getting this B9 prefix. So this will remain a mystery. but I still have it on my imaginary sheet of paper. I'm still trying to dig down that rabbit hole a bit. Maybe eventually I'll find out, and maybe not. But be assured, should I find out, you guys are the first to know. Right, so let's see what Della said. He told me that your program uses 4 to 5,000 instructions, which sounds much. Scratch without... Oh yeah, okay. How the program was written. Okay, but we talked about this yesterday. All right. Okie dokie. So let's switch over to this view. Let's go to here. And yeah, these are once more my super duper awesome and hyper amazing paint skills. But again, this time I at least used the line tool. So yeah, we need a nice color. I don't know which color should we pick. I think we start with the green. Green is nice. So just a quick summarization of what we did. When in our C or C++ programs, I still have the line tool enabled for some reason. The line tool is bad to write things, but writing with the mouse is quite hard anyways. So we're defining a variable that's called x, and x is an integer. And this grid is supposed to be our memory. All the gigabytes you usually have in your computer. These are just a few little bytes. There are 7F bytes if you want to convert hexadecimal in decimal. You know, this should be, I think this is 128 bytes or something. And yeah, I don't know. Calling them bytes or something is a bit not right, because we just say, yeah, this is our variable of type this, because in actual memory, yeah, no, or let's actually do this. Let's say these are bytes, and we have an integer called x. It's incredible that people make games only using the amount of memory you have drawn here. They don't. They use quite a lot more. They use all the gigabytes of memory your computer have. They are not only using those few rectangles I drew there. Those are just for demonstration purpose. So let's say we have this integer variable called x. Integers are, well, this is the reason why in Unreal Engine, I've said this so many times already, we are not using any of the standard C++ default primitive types, with two exceptions, which is bool and float, because what do you want to change with those? I mean, those are basically, yeah, it doesn't get any lower, right? So, and this is also the reason why in Unreal Engine we don't use just ints, because just by seeing this, you have no idea how large this value actually is. Is it 16 bits? Is it 32 bits? Is it 64 bits? Is it maybe 128 bits? Or is this a big int? Is this an integer that's many gigabytes in size because you tried to calculate pi up to the final digit or something? So for now, just for sake of this little chart and demonstration, let's say the int there, it's 32 bits in size, which is, if I'm not completely, it should be like 4 bytes. Is that 4 bytes? Yes, that should be 4 bytes, right? 32 bits should be 4 bytes, because 1 byte is 8-bit. And if you have 2 of them, you have 16, and you have 2 by 2, which is 32, which is, I'm completely confused, but I think it's 4 bytes, yes. So we have an integer called x. So the compiler, when he compiles our program, takes care that this variable can be stored somewhere, because the variables, we just put values into our variables, and we don't think too much about where these values actually are. We just take it for granted that, yeah, I have x, and I put a 5 into x, And at any other place, I want to get the value of x and I get my 5 back, or whatever. If I increased x in the meantime, I get like 7 if I increased it for 2 times or such. So the compiler has to take care that whatever we put into x, it has to be actually stored somewhere. So the compiler will make sure to reserve us a bit of memory. Let me just pretend this is the memory region we have. So let me paint this green so we know this is our x. And since x is an integer of 32 bytes in size, x actually occupies 4 bytes in memory. So, and these are our 4 bytes. The addresses, this is why this is such a neat grid and why I've written the numbers up there. The address where in memory it starts would be 1, 7, because look, it's in row number 1 and in column number 7. I'm not sure if you can, it's the same problem than last week. I'm not sure if you can see my mouse pointer, so I'm going to be trying to move it a bit out of here. So in column number 1 and in row number 7, this is, and we don't have, initially we don't have really to take care about this. This is some area in memory where the compiler said, okay, this is safe, here's some space, whatever you put into x, I will put it in here, somewhere in the gigabytes of your memory. And so if you ever want the value of x, the computer actually knows from where to get it. Well, because again, it has to be stored somewhere. The computer doesn't, well, actually he does have a really huge memory to remember stuff. That's why our RAM is called memory, because this is where the computer memorizes all these things. Oh, look at that. All of a sudden, things make sense again. Cheers. Yeah, need to keep my throat well lubricated so I can keep talking to you for, I don't know, quite some time. So this is where it is, and yeah, let's say I put the 5 in there. I write it down back. I write it here. I'm not sure if you can read it, but yeah, this is our 5 basically. I put it in here because, and this is another thing you really usually don't have to worry about. There is something that can be very, very confusing, which is called endianness. I'm not sure if I pronounced that correctly. I even have problems typing it correctly. But there's something like big endian and little endian, which is basically the order the bytes are stored in. Because again, this is a 32-bit integer number. It doesn't fit into 1 byte. We need 4 bytes. So the combination of those 4 bytes gives us our x value. And it's not like addition, because if we would just add them on top, it wouldn't make sense. We'd have so many ways to produce duplicate numbers. Because if I add a 2 and a 1, this is pretty much the same as adding a 1 and a 2, or adding a 1, a 1, and a 1. Get my point? So those bytes are actually interpreted like they are, being side by side, and then taking all the bits at once and interpreting this as a number, which the CPU does this. So this is, I'm only skimming over this because this is going really, really low level, and this is really something. This is something we usually don't even have to take care about when we are using pointers. Even if, well, and then you might, but this is really a fringe case. The danger of you actually getting in a situation like this is very low, and I think if you find yourself in a situation like this, I think you know what you're doing, so this shouldn't be a problem, because usually you do not access your memory this low level. You do not access your memory byte by byte. Like if you have a memory region where your integers are stored, or let it even be strings or anything else, you usually don't access your memory byte by byte, so you really don't have to care about this. Just so you know this exists. There's these things like little endian and big endian, which is again the order of bytes. Usually when we just write our numbers in binary. Remember, back in school where we learned binary. Let's do a fairly simple example with a 4-bit number, like we have 1 1 0 1. This is, let me see. Let's manually calculate this. This is 1. This is 2. This is 4. This is 8. So this is 12. This is 13. This is actually 13. I think. 14, 15. Yeah, makes sense. This is 13. 1 1 0 1 in binary is 13. We can forget about these again. These were just notes for me to manually calculate the decimal number. And again, this is now only for explanation and demonstration purpose. Let's say we got our boundary here. We got 2 bits each. Usually bytes are 8 bits in size. Let's pretend just for a second our bytes would be 2 bits in size. So this is a bit more easy to demonstrate and to explain it, instead of having to deal with this immensely large numbers. So just for the moment, pretend our bytes were 2 bits in size and not 8. So we would still have our 13. And this is actually the proper order of bits you would expect. You would expect the bit with the highest value, which is this first one here, be far at the left, and the bit with the lowest value, the lowest value, you know what I mean, is at the far right, because this one is worth literally 1. And this one there, is worth, what's it? 8. Because this is binary, so if this one is set, it counts as an 8. Well, because doing binary to decimal conversion. So and these are our bytes, and they are also in the proper order. The higher value bytes are to the left, followed by the lower value bytes. This is also what we just pretend is happening here. But then, and I also confuse this. I never know which is which. Let's, you know what? Let's fire up Google and look for little endian. So, which is, and maybe I'll be getting this in a language and can actually understand. Boop. This article has multiple issues. Yeah, we're not here to talk about the issues. So, okay. And this is what we've just done here. If we write the bits pretty much exactly like they turn out in a calculator. If you have a calculator like I can try to open the calculator. Let me open this one. So. And in decimal, I punch in the 13, and we go to hexadecimal. To binary. This is 1101. This is exactly the order in which, like, the calculator displays it in the order in which we actually expect it. Because also in decimal, the further a digit goes to the left, the higher its actual value. Because if the 1 is here, it's like 1. If it's there, it's like 1,000,000. 1,000,000 is way more worth than 1. So, and pretty much the same in binary. Unless you got a system that's in little endian. And this is, I'm not sure about the ARM processors in modern phones, but on the Sony PSP, for those of you who remember, I think the Sony PSP was little endian. And this is very, very confusing. And this is, it's kind of a killjoy. It kills you fun sometimes, because in little endian, this would actually be, the bytes are reversed. So the effect is the bytes are reversed. If I would be to write 13. Okay, no, let's start the other way around again. If I write 13 in big endian, I go, these are our bytes, right? This is the first byte with 2 bits. This is the second one. And first comes the higher value byte, and then comes the lower value byte. So this is our 13. And everything is cool. This is exactly what we expect. This is what we know. This is very intuitive. Now comes the unintuitive part. In little endian, first come the lower value bytes. So first the 0, 1, this here, because this is the lower value byte. And then comes the next higher value byte, which is 1, 1. And again, here's the boundary of our bytes. So this is also 13 in little endian, but if we interpret this like we know, like our numbers work, the more to the left you go, the higher the values. This actually looks like a 7. And this is something that can be very, very confusing when you actually go through your memory byte by byte, or in any size that your stored data is actually not in. Because if you just access, and even if you do it by pointers, we've seen this last week, and we're going to take a look at this week again. If you have a pointer and you add 1 to it, you're not literally adding 1 to it. You're adding the size of your value to it. So in case of our integer, we added 4, because the compiler knows, yeah, you have an integer there, that's 4 bytes in size. So if you add 1 to your pointer, you want to go to the next integer value, which is 4 bytes further in memory. So it actually adds a literal 4. So we would get at this spot in memory and not this one. Which we did. We tricked the compiler in actually just adding a literal 1 by changing the type of our pointer to something that's only 1 byte in size. And then we actually got well, we had no idea what we got. We got a pretty surprising number. We had no idea where it came from. It was just there. So yeah, you can do this, but I think the chance for you actually coming into a situation where you actually have to bother with this is very, very, very low. Usually in modern days, you don't have to bother with this, because if you have to, if you really go so low, because this is like super low level. This is as low level as you can get. You're directly byte by byte accessing your memory and then doing stuff with it. Maybe when you're dealing with encryption, when you're implementing your own encryption algorithm, maybe you access whatever data you have, completely ignoring the actual type of the data. You just encrypt your memory byte by byte. Then you might need this. But the chance, if you really ever need to do this, is quite high that in that case you also know, you quite well know what you're doing. So I think everything's cool. C64 is little endian too. Low byte first, then high byte. Yeah. See, this is, and especially on the C64, back in the days where we didn't have high-level sophisticated programming languages, C, and I'm actually talking C, not C++ now, was pretty much the highest you could ever have. There was nothing else, especially not game engines or stuff. Yeah, there were game makers, but they work a little bit different. So there you actually, on things like the C64, you actually had to deal with this kind of stuff. Fortunately, these days, in 99.9999874% of all cases, you do not have to bother about this. But now you know it exists, you have heard about it, and should you ever come into a situation where this becomes an issue, you at least know what you're dealing with, so you know what you have to ask other people about. Ask them about little endian and big endian, and then they will answer you, or I don't know, ask in the comments, or on Twitter, or wherever you like. Send a pigeon, smoke signals, whatever works for you. So yeah, you've heard about it. You know this exists. You know this can be an issue. But yeah, again, the chance of you actually having to deal with this is quite low, and you should be very, very, very happy that this is so. Because again, on the Sony PSP, the stuff I did back in the days on the Sony PSP, I actually had to deal with this, and encryption was, well, it wasn't really encryption. It was more like I did checksums and some scrambling of stuff. But I even did that with the integers. I even didn't do that byte by byte. I just used the integers, so I again didn't have to didn't have to care about the endianness, because I just said, yeah, I want the integer that's stored at that location, and the CPU already took care of demangling everything and using the right order, and then I got the value I wanted to work with, just like I needed it. But there were a few times where I actually was walking through memory areas byte by byte. But this was Sony PSP. This is also so long ago, and this was quite low-level, hardware-level stuff I did there. So yeah, fringe cases you usually don't have to bother with. The only part where you have to deal with it is when you use self-modifying code. Yeah, if you do, we had this. When we talk about, I think it was last week. It wasn't yesterday. It was last week. I think it was last week. We skimmed over self-modifying code a bit, and why it doesn't work these days anymore, which is, in a way, on the one hand, you can be happy that self-modifying code doesn't work anymore, because if it really can't work, nobody is attempting to do it, because by the laws of physics it can't work. But if it would be able to work, people would try it, and it can be a really, really pain in the lower rear, I tell you. But it's fun. It's all these things, especially also with pointers. I mean, going rogue and doing stuff in memory, and it's supposed to be. People like me enjoy this. I think this is great fun. So self-modifying code. People have done amazing things with self-modifying code that wouldn't have been possible without, for performance reasons. But well, this is a topic completely for itself. If you want to talk about this, please let me know, because we have one more Dev Talk left. We have one more Dev Talk left next week on Wednesday, where the topic basically is just sitting here and having a nice chat. You with me and I with you. So if self-modifying code is something you would like to talk about, and well, I can give you an example on paper, and with on paper I mean in Paint. And that's it, because as said, it doesn't work these days, because CPU cache. Yeah. So, well, if you want to talk about it, let me know. So we can do this next Wednesday, which is our last little Dev Talk session for a while. Because after that, the wonderful Game Dev Show with Stefan and Deborah will be back. And let's see what they got coming. They're building their new... Well, not Stefan and Deborah, but the Devcom team is currently building the new studio. I'm really looking forward to see that. And maybe one day I'll be able to make a session from there once all this pandemic stuff is done and over with, and we can actually go out and see physical people again, and not only the webcam images of them. So, back to the original example. This is our integer. This is our 32-bit integer, or x, and these are the 4 bytes in memory that x occupies, and we've put a 5 into it. So every time we now access our variable x, the computer remembers, okay, look, I had X stored at this location, so whatever is currently stored in this location, I will give you back, which in this case is the 5. So if we make a print on X, we get a 5. So now we talked about pointers. We wanted to have the address where this, for whatever reason, we actually want to know where our 5 is stored. We do not want to know the contents of our variable X. Again, my example was imagine variables like drawers on your table or something, or in your shelf or whatever. And you can open up the drawer and put a sheet of paper in. That's writing and putting a value into your variable. Or you can open the drawer and take the sheet of paper out of it again. This is accessing and reading your variable. So we can open the drawer, or actually we tell the computer, look, give me whatever is at X, and the computer knows, X, okay, this is the drawer, and it just hands us the piece of paper. We have no idea what drawer the piece of paper or what memory address our value was stored at. But we can get at this, and now even I can't see my my mouse pointer. If we put this ampersand sign, and you will see this in C code quite often, as well as the asterisk. If we do a print just on X, we get our value. We get the 5 that is stored somewhere in memory. We have no idea where it's stored, and usually we really don't care. All we care is the contents, the value we assigned to X. But if for whatever reason we actually want to know where in memory our X is stored, maybe just we want to do fancy stuff and try out things, we can put the ampersand in front of the X. This gives us the actual address in memory. In modern systems, not even the physical address, but some address. As an ex-professional paint user, the paint bucket tool is right next to the brush tool. Yeah, but that's too easy. Everyone can use the paint bucket. Mobile Curry, hi, a wonderful evening to you. Given you're in the same time zone, I don't know, maybe you're on the other side of the world, and then it's early in the morning or something for you. But anyways, hi. Yes, you're right. You're absolutely right. There's the paint bucket tool. But this would actually look like I know what I'm doing. Everyone can use the paint bucket tool. It's way more fun to write things with my mouse onto paint. This is something I really this is one of the rare moments where I wish I had like a graphics tablet with a pen or something, just for this writing stuff. So if we do a print, that was your contribution to this stream. Yeah, and you're right. You're absolutely right. Maybe I should actually use this. It would even preserve the lines, so we can still determine the rectangles. So yeah, I will keep this in mind. So if we do a print on X, we get our 5. If we do a print on ampersand X, in this case we would actually get, well, and let me prefix this with this O and the lowercase x, because this is a hexadecimal value I'm writing now, 17. The 5 is in decimal, but this really doesn't care. 5 in decimal is 5 in hexadecimal, so this really doesn't care. But this is, and this is the reason why computers like to use hexadecimal, which is basically a handy representation of binary values. It works rather well because they are aligned at those bit boundaries, so they pretty neatly match up. So if we do a print on the ampersand x, we get the 17 back, because this is here's the 7 and there's the 1, because this is the address in memory of the computer, and all the gigabytes of memory you have. This is the address where the x is stored. And now we can do fancy stuff like we can have another variable. Let's call it y, because why not? So, but we put the asterisk in there. So, and we discussed this last week, so I will again, I will kind of just summarize this because this is the stuff we actually did last week, and what we're building up upon. So this here, the x is an actual integer variable. We just put stuff in there and we're done and we can get it back. This is our 5 stored there. Cool. We're okay with that. Now we put the asterisk in there. This means y is not an integer value like our x. X is some random whatever integer like 5. Y is not an integer value. Y is a location in memory where an integer value might be stored. So this one is basically like this one. And again, also this has to be stored somewhere, and maybe I should have made the y in a little different color so we can determine which is which. So this looks like super nice now. And let me try the paint bucket tool. And the compiler said we said in our code, look, I want to have an integer variable x and I want this integer pointer called y. And the compiler said, yeah, cool, I got 4 more bytes for you. Where I will remember whatever you're putting in there. Now, this isn't an integer value. This is the address of memory, like this 17. It's the address of memory somewhere over the rainbow in all our gigabytes of memory where an integer value might be stored. So if we do, well, we need the brush again. If we do something like we put an, what should we put in there? A 36. We just, and again, this is hexadecimal. Maybe I should. If we put a hexadecimal 36 into y, we're not actually putting the number 36 in there. This is the computer knows this is an address of memory. So it's actually, let me see, 3 is here and the 6 is actually this one. It's actually this one. But the computer, or the compiler actually, the computer later on does not, but the compiler, while compiling our program, knows, okay, this is supposed to be a pointer to an integer value. And the compiler knows integer values, at least in our example case here, are 32 bits. And that's again 4 bytes. So these neatly colored squares are, if we put a 36 into y, these 4 colored squares are the ones we're getting the value back when we're accessing it. And if we're only having a pointer, this is also something we took a look at last week, and we're going to be trying out the code. The example code we did last week for this, we're going to be trying this out again also. If we want to access the contents of this address, we have to put an asterisk in front of the variable. This is pretty much similar to what we did with the x. X was a value, but we wanted to know where this value is. So we put the ampersand in front and we got where it is and not what it is. If we have a variable that tells us where something is, we just get the where something is. But if we want to know what this something is, we have to put the asterisk instead of the ampersand in front, because the ampersand is you have something and want to know where it is. And the asterisk is, there's my mouse, the asterisk is you have where something is and you want that something. So if you would do a print on the asterisk y, I don't know, we would get whatever number, let's say there's a 7 in here, and then we would actually get the 7 printed out. And now comes one thing that will be very important, and especially when you're doing Unreal Engine. This is something that is, this is a mechanic that is super important and you will be using very, very quite often, almost all the time, Let me see. I can grab everything I need and the colors and everything. So again, we have our integer that is x, and we have a pointer to an integer that is y. Something we can manually do, and yeah, I think we did this manually last week, and today we will actually try this exactly the way you will quite often use this. But one thing we could do is we could say, remember when we wanted the address of x, we could put the ampersand in front of it. Well, this is a nasty one. So, but you get the point. Don't judge me for my artistic skills. So this is the address where x is stored, and y is an address where something is stored. We could basically do something like this. And yes, we absolutely can. We can put the address of x into y, because y is the address of an integer value. X is an integer value. With the ampersand, we get the address of an integer value. And of course, I can assign the address of an integer value to the address of an integer value. This totally works. And under the hood, this happens quite some time. And what I can do now is, again, when I want to access the contents of where my y is pointing to, I put the asterisk in front of it. And I can say, okay, I'll be putting a 9 in there. Just because I can. And I've actually should have taken a 6, because a 5 is way more easy to change into a 6. But let me clear this out. And now there is a 9 in there. And if I would put 2 of these in there, I would have 9, which would bring me directly to Brooklyn 9. And I'm really hoping that Netflix will update their catalog with seasons 6 and 7, because I really want to see them. What if I put the address of y into x? Can you dereference y? Oh, you know what you're talking about. You seem to know what you're talking about, because even I don't know when to use the term dereference. That always confused me. Can I put the address of wait? Can I dereference x? Well, y? Okay, x. Maybe ask that again and actually put the x where you want, because I'm not sure which one of the y's should be an x. Can I put the address of y into x? Well, I'll try it out. Well, you can put the yes and no. You can put the address of y into x, but it won't be an address anymore. You can't just do x equals ampersand y. That won't work, because the compiler would tell you you're trying to put the address of something into a variable that's just a value. That wouldn't work. You could cast it. You could cast the address of y into an integer, and you can save that into x. That works. But then it isn't an address anymore. Then it's just a number. It's just a number that by coincidence is also the address of something, but to use it as an address, you'd have to recast it into a pointer. Aren't the addresses just hexadecimals? Technically, yes. Technically, the addresses are just, well, technically they are also only integers. Monogenesis, hi, greetings to you, a wonderful evening. Hi, nice for you to stop by. Hope all's good on your end. Yes, the addresses are basically just, you want to derail this? No, it's okay. Asking questions, perfectly fine. This is why we're here. No derailing. I think it's a relevant question to this discussion. It absolutely is. It absolutely is. Technically, of course, addresses are just well, depending on your platform, a 32 or 64-bit integer number. The compiler, however, has quite strict typing. The compiler knows that x is a value. And the compiler also knows that y is the address of a value. So even though technically you might think it works, and actually it should, you think you could do something like this. Technically, there really is no reason why this shouldn't work. The compiler won't let you the compiler won't let you, because the compiler knows this is not the address of something. This is the value of something, and this is an address of something. So what you'd have to do is you have to tell the compiler, okay, look, I want the address of y, and then you'd have to cast this back to an integer. And this is C style. This is not C++, but C is, again, as usual, quite more simple. You'd have to tell the compiler, okay, whatever this is, try to make a simple integer. Actually, you might even want an unsigned integer. This is supposed to be a u. Whatever this is, but well, x. Now forget this. X wasn't defined as unsigned integer. So whatever this is, try to make a simple integer out of it. And if that worked, put that into x. And since you're absolutely right, addresses are basically just numbers, this works. And the compiler will do this for you. The compiler will say, okay, I can do this. I can change the type of this into an integer. The value of it will actually be the same. So if you do a print on the ampersand y, or if you do a print on the whole casted thing to an integer, you will get the exact same result. We actually did this last week. We actually did this. Somewhere down here, I think we did this. Yeah, here. We actually did this. We saved the address of A into B. So basically in the code we did last week, A is what in my current example is X, and B is literally what Y is. See, A is an integer 32 and B is the address of an integer 32. And P is just a 64-bit integer. Because on modern computing systems, pointers are, as you just said, just 64-bit large numbers. So what we did down here is we put the address of A into B, which worked perfectly fine because B is the address of something. And then P is just a simple 64-bit integer. We wanted whatever is in B to have in P. So we could then just print it out. And for this, we actually had to cast this. And this is the C++ version of a cast. This is, well, this looks like a square root, which is definitely isn't. And where's my, let me erase those because they are not necessary. You can do them, no harm. No harm there. You can place them, but you don't have to. They are simply not necessary. So this is the C-style version of a cast that makes the address of something into a simple integer, and this is basically the very same thing. It's just the C++ version of the very same thing, because C++ is like, haha, I need to be way more complex because wait, my cable. Because I'm the next best thing. I have to be more complicated. So this is why, well, whoever invented C++ was thought like this is how it's supposed to be. So this is how it's supposed to be. And we are doing exactly this here. We're making a simple 64 integer out of b, and then we printed them out, and we will be doing this. We'll be running this again, and we'll be looking, but we shouldn't be running this, at least not like so. We might run it like this one, because this might actually not crash. The first one previously, that definitely crashed. And then we printed the contents of b, and we printed the contents of p, and they were both the same. Yeah. I hope this answered the question. If not, just, I don't know, ask more. But yeah, so it's basically the only reason why we just can't use pointers or addresses of something as simple numbers is because the compiler doesn't let us, because the compiler knows the types of every value, and C compilers are very, very strict with their typing, which is a good thing. There's languages like PHP that don't care at all about typing and what types something is. So you get into a situation where 1 + 1 is 11. And I'm talking decimal here, not some weird system, number system. Yeah, so the strict typing is a good thing. Saves you from many headaches. What we could do is, in this example, we had x, we had y, which is the address of an integer, and we put the address of x into y, and then we access the address that's in y, and we put the 9 in there. So up here, at first we had the 5 in there. Remember when I still had the 5 written in here? Oh, you're welcome. You're welcome. I hope it was clear, because the one thing that's pretty much as complicated as understanding pointers is trying to explain them. So I hope it made sense, and I hope it was clear. And if there's still anything unclear, please just let me know, and we'll see to find an answer. And if we have to Google for it, we'll find something. Well, not for everything. I still didn't find an answer to the B9 prefix, but well, maybe it was just coincidence. Maybe it was just the address. We will see today what we get. If we get something else, it was just a coincidence and it was an actual address, or I don't know. We'll see. So we put 5 into x, then we did all the address jingling, and at the address in y we put the 9. And if we now do a print, and let me shorten this by p, because I really want to I don't know, or PR or whatever, I don't know. And if we would now do a print on x, we would actually get the 9 back. Even though at first we put a 5 into our variable x, then we did some pointer magic and we added a 9 to some weird pointer thingy with asterisks, which totally looks like we know what we're doing. And if we now do a print on x, we all of a sudden get the 9 and not the 5, even though we never ever accessed x again. But this is because we accessed the address in y, which basically is the address of x, which is this 17 here in this case, this one. The cross marks the spot, the x marks the spot. Ah! I hate this. I really need to find another solution for this cabling. Because I keep ripping apart the cables and stumbling over them, and they keep getting messed up in stuff. I really need to find a new solution for this cabling. But this is there's nothing you should have to bother with. So we put the address of x into our y, which was the 17, and then we accessed the address that was stored in y, which is the 17, and we put the 9 in there. And so we could write something into x without actually accessing x. And this will become very, very important today, because today we'll be trying something out that's commonly known as pass by reference. Because usually when you call a function that is, I don't know, someplace, you just call it something, like the print function. This function usually only gets the values of the variables you pass it. Like, is there, I need a new one. Thank God I have so much paper here and I can just take out a new sheet of paper. So let's say we have an x that is 5 and we have a y, and this is a normal, this is just a value, this is not our pointer y. So this is totally confusing. Maybe I should name them a and b. It's less confusing. And this looks like a 6. Okay, let's put a 6 in there because I can't write with the mouse. And we have a b, and there's a 7 in there. And when we now have a function that we call, and we pass it a and b as our parameters that we want to pass the function, what the function is actually getting, it's not getting our variables, and it's always nice when these arrows look like smileys. I like that. What the function is actually getting is this. Because when we call a function and we put variables into the parameter list for the stuff the function wants to know, so it can do its job, it only gets the values that are stored in our variables. It has no idea about our variables. The function itself has its own variables defined or declared for these parameters. So the function will have own variables reserved and placed somewhere in memory, and copies of our, and this is the important part, copies of the values of our variables are put into the variables the function declared for itself as parameters, and then the function will continue working with its own variables with copies of our values. So whatever this function does with those values and its variables where the values are stored in, we don't have to care, and we don't care, and it doesn't interest us, because none of that has any effect on what we're doing. And there's one special case where this isn't the case. Thomas! Hey, you understand only Bahnhof. Well, that maybe is because you don't have to understand this. Because you're the guy who makes things look nice and shiny. And this is for people who make the nice and shiny stuff do something. But hi, nice for you to stop by. Everything's good on your end. So there's one. Let's say the function said, okay, this what should we do? We had x and y, we had a and b. Okay, the function said it has c and d, and for the purpose of this example also an e. So, and then we got the curly bracket open, there's code in here, and we get the curly bracket close, which looks totally like a curly bracket. So this is what the function, what if a function needs a complex data structure as a parameter? Will the entire data structure be copied as well? Very good answer. Very good answer, and we are actually going to look at this today, because a complex data structure or a complex object like an actor we spawned are pretty much the very same things. And actually what I'm just trying to talk about already goes into the direction of answering exactly this question. Because no. Spoiler alert, no it won't. Short answer, the short answer is it will get a reference to the original data structure and not a copy of it. And of course there's some danger in this, because why not? I mean, we're doing C. What would be C without any data? But this is something That's the case for higher language, higher level languages like C# and the likes as well. But yeah, this is actually, we're going to cover this actually. And it starts here. Because I just said the function has C, D, and E, and it just, so let's put a 9 in here for good measure. You can't read it anyways. So, and this is only considering, because this only works with the primitive types like integers, floats, and bools. Because as we discussed last week, everything we pass around, every variable we use, can only be as big so it does fit into the CPU register. Last week we talked about also a bit about how the CPU actually sees our code and how the CPU deals with values we are using with our variables. So if you've missed this, this would actually, I think, a quite good to look at, because we talked about an hour or so how the CPU sees our values, our variables, and why every variable we need, or the contents of it, has to fit into a CPU register. So this is only considering simple integer numbers, simple primitive types that perfectly fit into a CPU register. But the complex data structure thing starts here actually, because as said, this will get copies of the values we put in there. And then there is this call by reference thing. And in a function definition, you will sometimes see that in the function definition, you get this very crudely drawn ampersand sign that almost looks like an 8, which it isn't. Let me try this again. Where's my mouse? Here's my mouse. Yeah, this looks better. Huh? This looks way more better. When you look at the definition, how the function is defined, you sometimes will see that there's this ampersand sign in front of a parameter value. These parameter variables are no difference when the function itself says, oh, I also have a integer value of z somewhere here. These variables defined up here are very much the very same as the ones defined down here. There is technically absolutely no difference. They work and behave even under the hood, the stuff we don't see, exactly the same. The compiler for each and every variable will see that it finds a memory location where these variables can have their contents stored in. So like for this C, the compiler will say, let me pick a nice color for this. I don't know, let's take this one. Let's say for this C, let me color this here as well. Yeah, I think it's visible, right? This C will be stored here, 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 and there, because it's a 32-bit value, so 4 bytes. Then we got the D, and the D will be stored here, 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 and there. And then we got the Z. I've used the green. I think I'm running out of colors. We got the Z. Yes, I'm skipping the E for now. But we got this Z here as well, which will be stored there, 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 and there. So these are the memory locations where the variables of this function will be stored, just like we discussed before. But this E will be different. I'm different. It's like with this one special turret in Portal 2. I'm different. This E is different. Because, as said, the compiler reserves memory space, own memory space for each of those variables, except for the E, because the E has the ampersand sign. The compiler will skip the looking for memory part for this E. And it will use the memory address of the variable you called this with. This is also the reason why a parameter that's defined as call by reference, you can't put just a number in there. The compiler will tell you, this won't work, you have to use a variable. Because let's say we are calling this, can't write an F, we're calling this with, I don't know, 1, 5, and our X variable. Okay? These can be variables as well, but we don't have some. So for the sake, to keep this example at least a bit consistent, I'm just putting numbers in here and I'm putting the X there. So there's C. C is this area here. And this is where the compiler said, okay, I'll be reserving this memory for your C variable, and there's a 1 in there. And then there is this 5 that gets stored in D, and D was this one. And Z is just a variable that the function at some place uses. There's nothing in there yet. And then comes the E. And you can see there's no green area here in the function memory because the compiler skipped the reserving memory part for this variable because it's just using the address of our X. It's just using the address of our X for the variable E in this function because of the ampersand. So for this function, C will be stored. Oh, where's my mouse? C will be stored up there in the red block. D will be stored in this orange block. And E will actually be stored in this green block up there where our X is. It's exactly the same thing as we did here. It's exactly the same thing that we did here where we assigned the address of X into our Y pointer variable. And then we use this to access this memory location. It's the very same thing. So when now this function f does something with the variable E, like it puts, I don't know, it puts a 4 in there. If then back here we do a print on our X, we get the 4 that this function has put into its E variable. Because the variable E inside the function and our variable X reference the very same location in memory. So whenever I change X, the function gets whatever is in my X. But also if the function changes whatever the variable name inside the function, in this case the E is, I will get whatever the function put into its E after it's done, back into my X. And this will be, in Unreal Engine we actually need this when we want to pass return values into blueprints. Remember, it's super easy and super convenient to make your C++ functions be callable from a blueprint. Super easy. Passing parameters to it. Super easy. Returning values back to the blueprint is basically also quite easy. But we're doing exactly this. We're doing exactly this here because the blueprint engine, it has some internal variables that it passes to our function, and this parameter is defined with the ampersand as by reference. So we're basically accessing the same memory address as some internal value of the blueprint engine. So whatever we write into this will, after our function is done, will be available to the blueprint engine in whatever variable it used for it, so it can then use our result values as return values and continue working with it. this is exactly how this works. This is why this in Unreal Engine, this thing is very important. We are using it almost all the time. And we can also use this, if we're not in Blueprints, we can also use this to pass return values back to another C function, because as in many other languages, a function can only return one value, unless it's an array. Of course, you can put multiple values in an array. Yeah, you can do that. I think it's not nice, but you can do that. But an array, again, is also one return value. And using this, like, let's say you have a function f2, and this has an a and an b, and then it has an %c, and an %d, and an %e. So what this function does is, it has the ability to return us 3 individual return values. Because we just pass 3 variables into here that we then use as the return values, where we know where we get the return values stored into. So we give the function 2 values it can work with, a and b, and we have 3 variables we have laying around. We pass them for these 3, and when the function is done, we have in these 3 variables that we pass to the function 3 individual return values. So using this, we can also have multiple independent return values for one function call. And this is why I personally like using this a lot. This is also why I use this for, well, there's in Unreal, there's 2 reasons why I'm always, with very few exceptions, I'm always using this way to get my return values, even if there's only one, even if I'm only getting one thing back and not like 3 or 4. Even if I'm only getting one thing back, but which I could just return as a simple return value like we're used to, I'm always using this way for 2 reasons. The first reason is, this way I will always be able to make this function callable from a blueprint. I will have no problem just making this function visible to a blueprint, and it will immediately work without me having to change anything. Otherwise, I would need to change the function so it doesn't return this. It puts the return value in here, and I have to change the other function that already call it. So I always use this. So even if I'm not planning for this function to be able to be used from a blueprint, maybe somewhere, sometime in the future, I want to. And I like to plan and structure my code so that everything that might happen in the future is easily possible, even if right now I think I will never be doing it. But I don't know, maybe down the road I will change my mind, and I want to do this. And this is how I like to do my code. Already considering the future, even if it's unlikely, but as long as there's a chance, this might, I don't know, this might be used from a blueprint for whatever reason. As long as there's even a chance, I'm using this. And the second is because this just allows me to extend this and pass more individual return values. So this is why I kind of like this. And to spoiler a bit into the detailed answer for the data structures. Let's say you have a data structure. I don't know, some struct. Let's call it, well, struct. I would say str, but that could be string. So we have a struct. This is a bad name for a variable. Let's call it. I don't know. Let's call it bzyn. I don't know. I'm super creative with my variable names. So let's say there's a complex data structure in it. Classical struct, Well, we do have structs in C++ where we can make up literal data structures with individual properties that we can fill with things. And if you then have a function that you want to pass this data structure to, and this is something we're seeing a lot in Unreal Engine. Remember let me just open this. Because an image says more than 1,000 words. Let me just quickly open up our Game of Life project that we did recently here on this channel. Because again, an object, an instantiated object, is kind of very, very similar, if not even almost the same, like a complex data structure, because an instantiated object is a very complex data structure. So is this our Game of Life? Yes. Let's wait till this is loaded. Cheers. Thing is, I'm not sure if we're actually calling something. I'm not sure if we're actually calling something with a reference to our instantiate actor. I always see I'm quite side heavy. Let me come into the middle a bit. So the game, there's our actor, here's our cell handler thingy. Okay, this is an example. There's the tick component, the component tick. This is, but I'm looking for something that we might have. Yeah. Oh, haha. Oh, we did. Oh, look at that. Great. We actually did exactly this. Moongen and this. Good news. We absolutely totally did what he was asking. We passed, not out. Passing out on stream is something bad, I've been told. So I try not to do this. Okay, I'm getting silly again. So look at that. We got our spawn parameters. And spawn parameters, if we peek into this, is a struct. It's a data structure that's called fActor spawn parameters, and there's all the properties that thing has. Quite a lot. So, and we have a variable, not a pointer or anything. We just have a variable that consists of this data structure. Super duper. And if we go to the spawn actor, yes, this is exactly what I was hoping for. Great. And we did pass this. Remember, we had our spawn parameters up here. It's a variable. It's not a pointer or anything. It's a full data structure internally. And this is again this is basically a convenience the compiler does for you, because internally this is handled with pointers and things and thongs, and unfortunately the un was unwanted. Fortunately, you don't have to bother with this. You just say, look, I want to have a variable that holds this data structure, and we could just put values into this data structure. We set the owner, we set the no fail flag, and everything was cool. And eventually we called this spawn actor method, and we did actually pass it our data structure. And now comes your question: is a whole copy of this data structure be put into another variable in this function, in this method? No, because look at the definition. If we jump to where spawn actor is actually defined, here's the parameter. Spawn actor parameters, spawn actor. Well, yeah, the name repeats a bit. But look at this. There's our ampersand. And this is exactly what I was talking about right there. It's this ampersand it's exactly I'm not sure. Can you see I can barely see my mouse pointer. I need some. Well, we're not doing much paint in the future anyways. This is just to scribble stuff. So this is exactly this ampersand that I was talking about, I don't know, the last hour or something. It's exactly this. So this function has a variable that's called spawn parameters. It's pure coincidence that ours is called spawn parameters as well. We could have called this anything we want, literally. We could have called this Schnitzelsalat or, I don't know, or Gamescom 2021. This is pure coincidence that we call this spawn parameters. The name does not have to be the same. The names don't matter. All that's important for the spawn actor function is it also has a parameter, or for its view a variable called spawn parameters, and what it's getting into this is, well, it's not getting it into the variable, but it's exactly what I was talking here. The compiler doesn't reserve memory for a variable holding the data structure. It's just using the memory of our variable. So our spawn parameters, they have to be somewhere all in the huge range of memory. This thing is stored. And when this method accesses its own spawn parameters variable, it's accessing the very same region or location of memory like I was talking here and showing there. So this is basically our x. We're passing this into the method, into the function, and it doesn't even know that this isn't a variable that's where memory isn't reserved for itself. It doesn't even know that the memory for this variable is somewhere outside itself and actually belongs to some other function. It doesn't even know that, and it doesn't have to. And in this case, in case of spawn parameter, it only reads from it. It doesn't write into it. It doesn't use this to give us anything back. But this is the way you pass complex data. This is the way you pass anything that's not a primitive type. And primitive types are the integers, the bools, the floats. So the smallest things possible. And everything more like structs or objects or whatever else is always passed this way. So it gets the address of the other one assigned to this one and can then just access our data structure, which also has the danger if this method accidentally writes into one of these parameters, into these properties of this data structure. These properties are changed for us as well. This is something you also have to keep in mind. If you are writing a function that is passed a data structure, that you only write into this data structure if you really want to change the data of whoever called you. Because if here some property of this data structure is changed, we will here have the other new values, which sometimes isn't what you want. So you have to take care that you only actually write to stuff you've gotten by reference when you want this information to be passed to whoever called you, or you have to take care that you make copies of those values yourself so that you can manipulate them and do stuff with it. What would happen if the ampersand would not be there? You'd likely get a compiler error. If this ampersand would not be there, you'll get a compiler error because the compiler will tell you, look, that's not working. It's not working like this because it has to be this way. So it won't compile. And this happens to me quite a lot, especially with the, do we have the ulogs? No, we haven't used the, but we've used it here. This happens a lot to me when using this uelog macro, because you see there's the asterisk in front of this message. Because, well, yeah, F strings are again a bit weird, but it actually wants to access whatever is there, and I'm really good at forgetting the asterisk, which does not work. The compiler will say, nope, dude, this is not how it works. Think again, and then let us try again. And since this happens so many times to me already, I already know the message. And when I see the message, oh yeah, okay, I forgot the asterisk again. And then it works, yeah. Because it has to be, it just doesn't work any other way. And the compiler knows this, the compiler knows its stuff. And it complains. It complains a lot. But at least I think this is a good thing, because the C compiler kind of forces you to do your stuff well. Because if you do things that might end up being problematic, the compiler will just refuse to compile it. If it's not 100% clear, or if the compiler isn't 100% sure this will A, work, and B, result in the desired result, it will error out and tell you, dude, no, think this over. Yeah. And again, I find this is, even if you, the compiler at least, this is optional, but for Unreal by default, it's configured this way. Even if you have a variable you're not using, like if I don't know, I have ij and I don't know, z or something. If I defined a z variable here as int32 and I'm not using it anywhere, the compiler will not compile my program, because the compiler will tell me, dude, you have a variable you have declared here, but then you're never using it. Make up your mind. Which, in at first glance, you think, why? What is so bad at an unused variable? I tell you what's so bad at an unused variable, because that happened to me as well in a programming language that didn't care. Yes, it's PHP. You define a variable with some name. And eventually down the road, you actually want to use this variable, but you mistype because you're clumsy, because you don't have your keyboard under control. You have one little typo in your variable name when you're trying to use it. In the case of the C compiler, you will know, because the C compiler will tell you, hey, you didn't use this variable, and you're like, hey, come on, I did use it. Look, down there, I mistyped. All right. You fix your typo, you compile, and everything works. In a programming language that doesn't care, you start your program and it completely misbehaves and gives you the weirdest results that you really did not expect. And you're asking yourself, why? And you're looking through your code and you can't find the problem, because some typos are really hard to find. And like, I don't know, an hour later, if you're lucky, if you're not so lucky, a day later, you finally notice you had a typo in your variable name. Things that just do not happen when you're using a proper compiler. Yeah, this just as a little anecdote why I think, because I think for me it's, and I really encourage you to, this is why I even beg you to ask, because I think the why is always important. Why is something the way it is? Don't take things for granted. Don't say, oh, well, the compiler's a bitch. He always complains when I end up using a variable. Oh, this goes in depth. Don't take this for granted. Why? Why is it the way it is? I think, in my opinion, this is one of the most important questions you can ask. Why is it like this? Understanding why things are the way they are is, in my opinion, very important, because once you understood these things, well, you know why these things behave like that. You know why some problems arise, or why things don't behave the way they do, or you just know, okay, the compiler's not trying to bitch around. He's actually telling me something that might be very important and prevent me from having a really ugly bug in my program. So I can't stress this enough. Please always ask. There is no silly question. There is no bad question. There's no stupid question. There's one. There's in our whole world, there's only one. A literal one stupid question. And that is the question not being asked. I can't stress this enough. So, please ask. There's a hashtag above me. Use this. Use this goddamn hashtag and ask stuff. Use the Twitter handles down there. Tweet at them. You don't have even to ask. Just, I don't know, tweet at me. Like, I don't know, nice weather here. How's the weather on your end? I don't know. I'm a chatty person. I like to talk to people. So it hasn't always been that way, by the way. But anyway, we're getting off track. Let's get back to track. And Monogenesis, you're more than welcome. You're more than welcome. If you enjoy these streams, if you think this is your time, this is worth your time being here, then we're even. Then we're perfectly fine. So where were we? I think we were nowhere. I think field handler. You know what? Let me close this. It only confuses me. Let me close the Game of Life thing. If you haven't checked out our Game of Life, do it. In 3 sessions, we made a Game of Life implementation, which I think turned out quite nicely for, well, having it done here. And the source code is also available via Git, not on GitHub. It's on my own repository server, but the code for the Game of Life thing. The whole code I made here live during the 3 sessions is available to download via Git. To look at it, check it out, play with it, and ask questions about it. So, where were we? I think we had the by reference thing covered. Always like to learn. That's a solid base. That's always good. Dinner. Ooh, dinner. Okay. Well, enjoy your dinner. I had quite a good lunch today, so I'm fine. I have my orange and mango juice for tonight. Tomorrow I will have a wild berry mix. So Monogenesis, thanks for stopping by. Enjoy your dinner. And if your dinner takes longer than I will be here, then, well, see you around. I'll be back. And also, there's always the recordings that will be archived to YouTube, which might be interesting for some of you. All the sessions we're doing here, they will be archived for eternity on YouTube. And I'm also every now and then checking the comments if there are any on the videos on YouTube. So if you're watching this on YouTube and you have any questions, or you just want to tell me how bad I am at explaining things that I always take way too long to answer a short and precise question, just down there below the neat Twitter handles, even more below, there's a comment section. Go for it. Go for it. And like the video if you liked it. If you didn't, the other button works as well. And also push the subscribe button, because pushing the subscribe button is the only thing that's almost as good than pushing the skip ad button. Yes, the more you know. Okay, enough self-advertisement. I think we got the pass by reference thing covered. And since there is no further questions from you guys, I consider this covered. So this is how it works. So let's dive into some code and try a few of these things out. I think I can close those. Those are not that important anymore. Leave this one open for later maybe. So what we did last week, and I think we're just going to be running this. This was basically just, we actually looked at all the pointer stuff. We made a variable. Super hungry. Eat something. Yes. I don't even need to be super hungry to eat something. I just need to be, and this is actually a problem. I just need to be a bit hungry, and I start to eat something, so I'm not hungry anymore. But hi, nice for you to stop by. Want to get into IT, but can't choose what to do. No college degree. How does one get a job? Are coding boot camps the way to go? If coding boot camps are the way to go, depends on what kind of learner you are. There's different types of how do I phrase this so it doesn't sound too scientifical. There's different types of people and how they learn best. There's people who can learn quite well by reading something in a book, and then they know how it works, and then they can do it. That's definitely not me. Then there's people who just need to try, who need to be told, do this and that, try this out. And then you do it. And then you see if something works or not. And if it doesn't work, you try to find out why. This is more me. So it actually depends on what's for you personally the best way to learn, how you learn stuff best. It highly depends on that if a boot camp would be good for you, or maybe starting with some tutorials on YouTube, because they are quite nice, because usually they explain stuff and you can pause them and you can try out everything at your own pace. Like the tutorial says, look, if you do this and then that, this will happen. And before you can continue a sentence, you press pause, and then you try this. You try this at your own pace, and once it works, once you're satisfied and you're like, okay, now I want to know more, you can unpause the video and continue. This, at least for me, again, this depends on your personal learning type, but this, at least for me, is a quite good way to learn stuff. Not having a degree is actually these days, fortunately, not that much of a problem anymore, because more and more companies actually look at what you actually can do, what you're capable of doing. So what would be very important if you want to get a job in IT, in programming, or in whatever, learning the stuff you want, and then making stuff with your knowledge, like writing little example programs, or doing small projects. And then when you apply for a job, show them off. Tell them, okay, I've done this and that, so they can see the things you're capable of. And this gets more and more important than just a sheet of paper that says person X has a degree of Y, because Y. So this is then for the job seeking. X for Hi says hi, and to reply to Super Hungry Eat Something, you should try to learn a language in the field you want to go. Yes, yes, that's absolutely right. You of course should learn things that you actually need for what you want to do. Very intimidated by how difficult Reddit makes it to seem to get a job. Yeah, well, Reddit. Um, yeah, Reddit is just Reddit. Don't put too much value in stuff that's posted on Reddit. Of course, finding a job is not easy. I don't want to I don't know, nice talk this or sweet talk this. Of course, getting a job is hard, especially if you're new to the business, to the field. Like, let's just take me for example, because I'm not sure which direction you actually want to go. But for me, I've wanted to go into game development for ages would be hundreds of years. Let's say decades. For 1.5 decades, I wanted to get into game dev, which was almost impossible because I didn't have any experience in game dev. I wanted to make up. I wanted to on my off time during my normal job. I wanted to do little projects in Unity or in Unreal, so I'd have something to show off. Instead of, look, yes, I'm a super professional game developer. I want to work for you. Here are my references. Yada yada yada. I got this degree. I got that degree, which I all didn't have. I at least wanted to have some projects I could show them. So, look, I'm not a super pro. I want to get into this business, but look at this. I already can do something. Unfortunately, I never got the time to actually doing that. Because when you have a job, and when you come home, sometimes you just want to go to bed and you're tired, and then there was streaming, which also costs time. So I never, for a long time, I didn't manage to do this. But the job I was at, no, this might be a bit better of an example. The job I did at this time, when I still was dreaming about getting into game development, I also got this because I did have projects to show. I also didn't have a super fancy degree that at least would fit to the job I was applying to. In terms of something that's written and sealed on a piece of paper, I had almost nothing. But I had projects I had done in the past, be it just personal projects that I just did because I wanted to do them, or maybe even little projects I did in my previous job. So I showed them, look, these are the things I actually did. Yes, I don't have any degrees. I don't have any paper that tells you that I'm good at something. I only have actual projects that I did that might show you what I can do. And that was the reason why I got the job. So, long story short, learn the stuff you need for your dream job. Make up a portfolio. So have samples of what you're capable of doing, and then use those to apply for your job. Still, getting a job, still one of the worst things to spend your time with, finding a job. But in my opinion, this is only my opinion, you stand a quite better chance this way. Show off stuff you've done to prove that you're actually fit for the job, that you can give your future job giver, your future employer, that you have a value to them that they want to have. So yeah, whatever the direction is you want to go at, Try to get this stuff into your head, use it, and then use the results to make the others want you. That is the short story of, again, quite a long answer. I hope this helped a bit. I'm not sure if this helped. Oh, it was helpful. Okay, okay. I'm glad to hear this. Great. So fingers crossed, and all the best. Cheers. So, back on track. What we did last week and what we'll be building up upon. Relatively new to the channel, but must say, already enjoy the content. Oh, I'm very glad to hear this. Thank you. Thanks a lot. So, yeah, let's all have a good time. What we did last week is we took a look at all the pointery stuff. We actually just took a look at the pointers, at the memory addresses, and we will run this quickly to again look at it, and then we will try to build upon it and do things, especially what Moon Genesis asked before. Passing structures, we'll be passing the reference to an object, which is basically the same thing, which covers the pass by reference stuff. So the first thing we did. Oh, and thanks for the bits. Thanks a lot. Thanks a lot for 500 bits. Super hungry, eat something. Thanks a lot. So we just declared a variable we called a, because I'm so creative with variable names. And we just said, okay, this is a 32-bit integer. Nothing special. Super easy. And then we declared a second variable b, and there we got this asterisk, because while a is actually an integer value, like 4, 7, 9, 7 of 9, that was, by the way, not intentional. And b is not an actual integer value. B is the location in memory. Again, this is this little fancy chart. Is the location in memory where such a value is stored at. And then we had a 64-bit wide integer we called p, because we wanted to store a pointer value in there, so we called it p. And these were the three variables we declared. And then we put something into a, and then we put the address of our a, because again, this is what we talked in the very beginning. Our a, this 4 that we put into a, it has to be somewhere in all those gigabytes of memory your computer has. It has to be somewhere, and this somewhere, this where it actually is, we picked out with the ampersand in front of the a, because again, the ampersand is the address of something, and the asterisk is pretty much the same thing, but the other way around. This is super confusing. So if you feel confused by this, don't worry. Even I get confused by trying to even say how these things are called. So this is the address of something, and this is something's address, or the other way around. So it doesn't help. It stays confusing. So we took where the address in memory where our a is stored, and we put it into b, which works perfectly fine because b is an address of an integer, a is an integer, ampersand a is the address of this integer, and the address of an integer can be perfectly fine stored into an address of an integer. Fine. Then we wanted to have this address as a plain integer number, because these are pointers, and we this was a question that came a bit earlier tonight. Well, isn't an address basically just another integer? And technically, yes, but for the compiler, no, because the compiler has this very strict typing. The compiler knows that this is that whatever number is in here is supposed to be the address of something. So you can't just use this as a simple number, because the compiler knows, no, wait, this is not a number. This is the address of a number. So we have to tell the compiler, look, we do have an address of a number, but please make us this address into a number itself. And this is the long and confusing version of a typecast in C++, which basically just says, whatever type of this is, please make a simple 64-bit integer of it. This might work, this might not work. If it doesn't work, it also won't compile. So if this properly compiles, you're pretty safe. The compiler will notice this not working while compiling, because the compiler knows the type of B, and the compiler knows if he can actually make this out of that. In this case it can. So in P we got a actual simple integer number like our 4 or 7, only that this number is pretty much the very same as the pointer value we have in B, which we will see later on, because here we see the value that's in B, which is the address of A. So these two lines, in theory, should give the very same result. And then we got our P, and the P should have the very same result than the B up there. And then just to look around, we also looked where our P is stored and where our B is stored. So what did I do there? So this is basically the address of an address of something. Doesn't get better. It doesn't get any better with pointers. Because remember, in B, we have the address of an int32. So if we print the address where our B is stored, we have the address where we have stored the address of where we have stored an int32. Yes, this is a rabbit hole that goes down quite deep. And the thing is that we actually sometimes, and we might actually do this in an example tonight, that we actually have notations in a function definition where we want the address of an address of something. So do I have an example? Can I quickly can I give you a quick spoiler? Let me see if I. Yes, I do. Look at this. Notations like this. I mean, this looks still kind of neat. So let's make it like this, or maybe like this, where you have the asterisk and the ampersand for one variable. So this variable, this parameter to this function has to get it to the total confusion, it has both. It has the asterisk and the ampersand at the same time. So basically what we're getting here is the address of something. And this is what will be, I hope we got about an hour left, but maybe we go into some overtime. Maybe we make 1.5 hours. And this is what we're going to be doing tonight. This is one of the nasty things we'll be doing tonight. It makes a bit more sense when you write it like that, because then you know this is passed by reference. So I get the address of something, and I actually want just to store this as an address and not as something else. But this is going to be fun. This is going to be really, really fun. Yep, pointers. They're fun, aren't they? They are always so much fun. So if next time you're at a party and you have absolutely no interest in talking to other people, you just want to be for yourself and wait for the party to end, start talking about pointers and everyone will just leave you. Let me just refill my juice quickly. And then we actually run this and we look at all the values just so, I mean, we've talked about pointers for so long now. Let's actually see some, right? It's like when you're at the fourth date and you still haven't seen her the way you want. So let's get them seen. So this is our A and all the stuff. And oh yeah, here's the ampersand thing. The asterisk. See, I'm already totally confused. Because as I demonstrated here on my super fancy paint skills, if we have a pointer to something like our B here, could you show some scenario where pointers come in useful? In Unreal Engine, you're using them all the time. And also, when you're passing anything that's not a primitive type, anything that's not a simple integer or bool or float value, you usually pass as a pointer. So pointers are pretty much always useful. You literally can't live without them. But you also can't live with them. Because they just ruin your sanity sometimes. But we're doing some examples today. Of course, they are only examples. But wait, I can show you one thing where we actually... Wait, let me open up the Game of Life thing again. Because I can actually show you one thing where we actually actively, usefully used pointers. You're a C# dev, so no pointer knowledge. Yeah, because you're lucky. C# takes care of everything. Because internally there's a lot of pointering in C# as well. You just it just doesn't bother you with it. It takes care of everything for you. But even in C#, if you pass an object as a parameter to another function, internally it's passed as a pointer. But that's all done internally. So you really don't have to bother. You don't have to worry about this. You don't have to worry anyways, because I've seen seasoned C++ or C programmers, guys who did this, I don't know, 30 years of their life. They basically only did C and C++, so they really knew what they were doing. And even they get confused with pointers. So there's a saying that I made up by changing a different quote. This quote originally comes from some other topic, but I think it fits perfectly good to pointers as well. It goes like this. Who says he has understood pointers has not understood pointers. It's as simple as that. So where's my cable? No, not the cable of the mouse. So this is our Game of Life, and just for the sake of doing it, let's run it. Look at this. We did this for 3 weeks. We did this, like we got done with it. Why are you not? Oh, it's crashing. What did I do wrong? Okay. Close. Okay, we're not here to debug this. I just wanted to show you something. I have no idea why it crashed. Maybe I did something wrong last time. See, this is cliche. It worked yesterday. Well, it wasn't actually yesterday. It was the last time I tried it. It actually did work. I have no idea why it doesn't now, but we're not here to find this out. I want to show you where we actually used pointers. So where's my Game of Life? There's my Game of Life. Let's open the code of it. But C# is quite nice. I personally like C# a lot. I do Unity development as well. And well, Unity is C#. And I've also used C# without Unity. And I really like C#. I think C# is a very nice programming language. I enjoy working with C#. It's very convenient. It's very convenient, but yet it offers you quite a lot of functionality, quite a lot of things out of the box that are just there. The standard library that C# offers you has so many useful things that you can just use instead of having to come up with your own solutions. So yeah, I like C#. I actually like it a lot. Now, especially with .NET Core and ASP.NET Core. Yes, the .NET libraries, then again, they have so much amazing function. There's so many cool things that are in there that you can just use. And yeah, I'm absolutely with you. I'm absolutely with you. So pointers, look at this. This is where we before it just crashed. I think this worked without crashing. All these little dots you see here, that when you click on them, they become those larger cubes. Those are individual actors, as you can see here. They are all spawned, and we spawned those actors at runtime. We didn't drag them all into the scene because, I mean, look at it. I mean, I was just too lazy to do this, so we made the program do it. See, scene originally is quite empty, and the actual line. Well, this is a loop because quite a lot of actors we had to spawn, so we had to do some looping, and this is the actual line that spawns this actor. For those of you who are more familiar with Unity, an actor in Unity in Unreal, an actor in Unity is basically okay. The way I use actors here is like you would use a prefab in Unity. The actor is basically a game object. But there's no difference between like Unity makes a difference between things that are in the scene and prefabs that can be in the scene. There's no such difference in Unreal. But X4 is familiar with the actor model anyways. So all right. Oh, using Azure, nice. Yeah, so basically, again, but quickly for your Unity guys, I'm using this actor basically like you use a prefab in Unity. You can also spawn your prefab somewhere in the scene, and this is what we're exactly doing here. We spawn the actor. This is just the location, and this is some more parameters. We had this as an example a bit before for the question, what if I want to pass complex data structures? Because this is one, it's not that complex, but it's a data structure. And look at this. This is it's just returning this. Okay, it's just returning this as a simple return value. But let's take a look at the definition of this method. So see, this is the spawn actor method, and these are all the parameters we pass to it, and this is the return type. And you might already notice the asterisk here, because again, you can't pass anything around that's not one of the simple primitive types like integers, bools, and floats. Well, not like, that's it. Because, and we covered this extensively last week, in C or C++, everything we pass around must be able to fit into a CPU register. Again, long exhaustive explanation for this in last week's video. So the spawn actor method returns us a reference to the actor we have spawned. So once the actor is spawned in the scene and it exists, we get a reference back to this actor so we can then things with it. Like, I don't know, move it, call methods, or whatever we want. And a reference is always a pointer. A reference to something is always the address of this something in memory. It's just differently phrased. Saying I have a reference to something is a bit more understandable and a bit more intuitive than saying I have the pointer of something in memory too, where it's stored. But having the reference of something is just another wording for we get a pointer to it where it's stored in memory. And this is what the spawn actor function returns it. Since it can't return us the whole object, it can't give us the whole actor, because the whole actor object really doesn't fit into a CPU register. So it has to give us the address of this object, which in this case is an actor, and an address of something is a pointer, which is it's this asterisk there. All 2Pixel knows is Java, and even that is a little bit. Yeah. Java is. Well, we just had it about C#, and C# is what Java ever wanted to be. Yeah. Oh, no, I got it. You just know a little bit of Java. Okay, now I got it. Okay. That comment style is clean. Epic will be glad to hear this, because this is actually this is an actual source file of Unreal Engine we're currently looking at. But I try to have it kind of like this. I have to admit, I have to try a bit harder to actually get it like this. But yeah, this is the commenting style you want. This is a very good example. Well, X4, thanks for asking. This is why we're here, right? So yeah, it gives us a pointer, and we're receiving the pointer back into this variable, because this variable, again, if we look up here, is declared as an actor pointer. So this is our variable, so we can get. Why was I not able to scroll there for a second? So we get, as return value from this method, we get a reference to the actor we just spawned, and we store this away. Actually, not quite. We call a method on it because our actor has. And don't judge this comment style. This was just done in the course of this tutorial. This is not supposed to be production code that is done with all best practices in mind. This was just showing how stuff works. So set coordinates, which is this one here, which is just this one, and we're calling this on our actor that we just got back, and then I think we're storing it. We have a 2-dimensional map, and we're using this map to keep references to all the actors we spawned, so that later on we can loop through our 2-dimensional whatchamacallit from now I'm completely lost. We can loop through our 2-dimensional map to access back the actors that we have stored in there, which again are the pointers. So we can use the pointers to all those actors to then do stuff with them, like call this method, and once we've done that, we call this method eventually. So yeah, this is the question was an actual case where it makes sense to use pointers, and this is actually where in the course of this tutorial series we made this little game of life implementation where we were actively using the pointers to the actors we got back, to store them, to retrieve them, to use them to access the actors they reference. But basically in C++, I just said it, you can't live without pointers. It's also quite hard to live with them, but you definitely can't live without them, because everything that's not just a simple primitive data type basically has to be passed around as a pointer. And you think you got it. Cool. Nice. I'm from Germany. Yes, I am actually from Germany. Did you determine this by my horrible accent? I hope not, because I'm trying to not have that much of a horrible accent. Or did you scour the internet and got all the information about me? Now, you couldn't have done in that much of a short time. There's too much information. Oh, supported by NRW. Does it say supported by? Oh yeah, up there. All right. Yes. Yeah. Yeah, it's Devcom. Devcom is supported by NRW because Devcom is located in Cologne. I'm only a guest on this channel. I am not Devcom. I'm just a guest on this channel who can have a nice time with you and do stuff. So let's try this out. Yeah, it's actually my accent. Okay, this means I have to practice more. I see. Okay. This is valuable feedback. So starting tomorrow at work, I will only speak English. Fortunately, we have one of the guys in our office is actually born in the United States of America. Back then, when when they were better. So, yeah. You're learning C++ at the moment and was told that the docs recommend smart pointer usage over primitive pointers. Haven't used them yet yourself, smart pointers. I gotta admit, I'm currently not sure what smart pointers are, but maybe Google knows that. C++ smart pointers. I gotta admit, I have no idea what they are referring to. Pointer. Smart pointers. What are smart pointers? Unique and shared pointer. So, give me an example. It's stuff like that. Okay, here you got your problem, and this is already the explanation why we're not using this in Unreal Engine, because this unique pointer thing is something that comes from the standard library. And there's one thing we're not using in Unreal Engine, and that's everything that's standard. Again, a hint that you're from Germany, your Google is in German. Yeah, there's no way to change this. I always get the German results first. And I also have to, change them or look more. Because actually, technical stuff like this, I really don't want to read in German. So yeah, this unique pointer thing is not actually a language construct. It's something from the standard library, and as said, there's one thing we're not using in Unreal, and this is by definition. This comes directly from Epic. We are not using standard stuff. We are not even using the standard int primitive. So we're not doing it like this. And you see, even the syntax highlighting makes this into a different color. We're not even using the int primitive. The only two actual basic standard C primitives we're using are bool and float. All of your libraries are unique. I suppose so. Well, I haven't written a library yet. I'm just using the stuff Unreal Engine gives me. But I am sure they took care of that. There's also one thing that I'm really looking forward of them implementing, because when you're doing C++ for Unreal Engine, you can't use namespaces, which is kind of sad because I like using names. I really got used to using namespaces. And in C++ for Unreal Engine, you can't use namespaces yet because the engine will get completely confused and everything will just crash. But it's on their to-do list. They want to add support for namespaces eventually. Unfortunately, it's very far down on their on their priority list. So not sure when those are coming. Yeah, but see, we're not even using the default int primitive. We are using explicit int32 or int64, which by the syntax highlighting you can already see are custom types. And the only actual C primitives we're using are bools and floats. Wait a minute, you're a dev at Epic. No, I wish. I wish. No, I'm not a dev at Epic. I just use Epic's Unreal Engine. And so basically it's coming from the engine. It's something the engine demands, and by proxy Epic wait, I have to sort this cable because my cable is always against me. No, it's actually it's something that's dictated upon you by the engine, and so by proxy by Epic, that you always everything only uses the special Unreal types. Even for ints we use them, which makes sense because if you just do int, yeah, what size is this int? How large is this? You have no way of knowing. It depends on the compiler and the hardware platform your program is running on, if this thing is 32 bits or 64 bits, which can lead to problems. So they have these explicit int32 and int64 types, so you know that one's always 64 bits, and if it can't, it won't compile. And this is always 32 bits, even if it's running on a 128-bit computer in 100 years or something. But speaking of, I'm actually I work at Spaceflower. It's the second of the two Twitter handles down there. I'm working at a small but yeah, a studio that tries to be less small, but yeah, a quite small studio located in Nuremberg. In C++, you have int32t and uint32t when you want a known size. Yes, maybe, I don't know. Maybe they only map those to. Oh, it's even more. Nah, they even made even more complex stuff. Typedef signed int. Signed long. Ah, whatever. Yeah, you can do that. But again, Unreal Engine tells you not to use them. For Unreal Engine, you actually have to use these. Did you know there were integers 32 and 64 bits? Yeah. Well, Dominic just said you in plain C++, you actually do have types that make a difference. But again, this is convention by Unreal Engine to not use them for everything. Really, absolutely everything except floats and bools. You always have to use the custom types supplied by Unreal Engine. Not even string. I mean, look at that. We even have a special thingy for strings, which I'm not sure if it's a whole object or yeah, it's even a complete object. and not your good old character array. You know, I sometimes oh, caps lock. Sometimes I miss the times where this used to be a string. It was so easy. They were easier times. Yes, they were. I actually have a question that has nothing to do with... I'm not sure. Should I... Well, a bit more earlier I said the only stupid question is the one not asked, right? Dominic, please allow me a question. Have you been at some time in the past known as under the name KDS Best? Or KDS? Is that in the realm of probabilities? Because that's a question that just popped into my head. So anyways, I kind of missed the times when this used to be a string, but they're not. This times it's this. But well, you get something in front. I mean, there's so many, you get so many convenience. I mean, it's like what you know from C#. I mean, if you have a string in C#, it's also a fully fledged object. Well, because everything, really everything, is an object in C#. And you have stuff like compare, equals, contains, and all that stuff. So yeah, but what we wanted to do, because we want to do something else, we actually want to create a new object. And the things I just showed you in the Game of Life thingy, that I think I can close again, just to open it up later again. I don't know. So it's this one. Let's see if we have this properly compiled. Yeah, we want to create an object, and we want to instantiate an object, and we want to get a reference to the object, and we want to pass the reference to the object. We want to do all these nice things. I even have to peek at my notes to remember what's all this stuff and where is it where we pass the where is it where we pass the wait at one point we look at that because I want to return it there. Okay. Oh this is neat. Okay. Oh yeah, we're doing some. Oh yeah, we're doing some nice stuff. All right, so let's try this. Hope it still works. And here we go. Look at that. This is the output of all the stuff we just had. This is our A. This is our variable A, and there's currently a 4 in it. The B9 actually. Okay. This solves the question for the B9. It just was coincidence where we got it actually wasn't a prefix. It's an actual address. Yeah, that's just a simple and actual address. All right, this explains why I didn't find anything in regards to the B9. Okay, what a coincidence. Anyways, we got our A, and A has a 4 in it. And then we got our address of A. That is where this 4 has to be somewhere in all the gigabytes of memory a computer has. This 4 has to be saved somewhere. And where this is this. This is the memory address. This is the location in memory where our 4 is stored. So if I would open a hex editor now that has the ability to access random addresses in memory, if I would navigate to this address, I would find our 4. Neat. So then the contents of B is the very same as our address of A. Makes sense because B is a pointer, and we just put the address of A into B. So these two being exactly the same not only makes perfect sense, but is also what it's supposed to be. It would actually be quite weird if they would be different. So then we have the address of B, because the address of A that we put into B also has to be stored somewhere in memory. And this is this location. And then we got P. P is just remember, B was, let me try to highlight this so you can actually see the matching numbers. B is a pointer. And this is compiler typing. You can't just B used as a number because the compiler knows it's a pointer. But we wanted to have it as a random number we can do random stuff with. So we cast it to a integer number that we then just put into P. And so the pointer stored in B is pretty much perfectly equal to the number stored in P. And that as well has to be stored someplace. We just wanted to see all our memory addresses, so we just printed out that as well. And now look at that. We got in A, we got our 4, and now we got a 7 in A. And this 7 in A happened without having accessed A at all. We just, this is what I scribbled down here earlier on. We just have our B, which is the address of some random memory location. Then we put the asterisk in front of that. So that means this is a pointer and I want to access the address. I actually want to access the address at that thing in points. And we just put the 7 in there. And so now A, since B holds the address of A also, no, not also, but A has the value of 7 without us actually having accessed A. So, well, you could use this in coming up with a copy protection, because people will say, where does this value come from? What else have you got? Not much more. Just a few pointers. And here we, one more thing we did is we added 1 to B. But we didn't get 1 more. We actually got like 4 more. Is that 4? Yes, A, B, C. Yeah, I think this is 4 more. So we did a +1, but instead we ended up having a +4. Because the compiler knows, and this is the typing thing, because the compiler knows B is a pointer to an integer, and he knows this integer is 4 bytes. So if you add 1 to B, it doesn't add the literal number 1 to the pointer. It adds one address, or it adds one address to it. So we get the address of one item ahead of this, which if you do this wrong can go really bad, because I mean, still we're accessing, more or less by coincidence, we're accessing memory that's located to our program anyways. So this is cool, we can do this. But if you're not careful, and we actually tried this last week, you can put an address in here that's beyond the memory you're allowed to access, and the thing just crashes. And this is whatever is stored at this address. It's 22E. I have no idea where that's coming from. But for some reason, at this address, we got 22E. Didn't we have a C? Oh no, this was the addition. Okay. Well, there's a 22E stored in there. Nobody knows exactly why. So, let's do another cool example. So let's hop into the Unreal. I hope I'm in the right one. Yes. I think we were in this directory, and just let's add a new C++ class and an empty C++ class default const. Exactly. That's what we're going to do. We just create a simple class, nothing special, no actor, no component, no nothing, and we just call this some class and hit the create button. Because what we're going to be doing now is we're going to be instantiating that thing to get an object, and then we're going to see what we get. So, and of course this opened in the wrong window. because why not? So, why am I not seeing the files here? What went wrong? Hello? I would like to see my file. There they are. Okay, it just took some time. Here they are. So this is our sum class. And this is the header of our sum class. So everything's fine. We got our constructor, destructor, nothing special there. Also, not much commentary to clean up. So let's start with having some method in here. Come back and watch the VODs. Yes. Oh, glad you like it. And by the way, just for info, these sessions, of course, you can watch the VOD. Absolutely, they are recorded, but Twitch only stores VODs for so long. So these sessions are also archived to YouTube for eternity. So even should you miss the VOD and Twitch might have already purged the VOD, it will always be there on YouTube. Great you liked it, and enjoy watching the VOD. And if you have any questions, you can use this hashtag up there on Twitter. You can use one of or both, I don't know, I don't care, of the Twitter handles down there. If you have any questions, please feel free to use any combination of the mentioned on Twitter to ask your questions, or post them on YouTube in the comment section of the videos. I'll be checking them every now and then and see if there's any questions. But these will immediately, the moment the moment you will use one of these, I will get to know, and I can try to answer. So yeah, have a good night. And in theory we're almost done, but I think we'll be doing some overtime again tonight, because I really want to show you this, and maybe finish off our discussions about pointers. So let's see what we're going to be doing next week, because honestly, I have no idea yet. So we have some method at first, and all this method does is, let me copy paste the UI log thing here, and maybe you start playing with Unreal soon. That'd be nice. So yeah, have a good night, and well, if you start playing around, tinkering around with Unreal, have fun, because that's the most important part, having fun. So we don't need this, and we say this is a method from some class. So we need, so we know what's called. We also have to add this to the header. I let my IDE take care about this. It's in the public section. Jesus Christ. Yeah, my accent is horrible. I have to. I used to be quite good in English, but then I didn't get the chance to use it for years, and now I'm horrible again. Maybe I need to watch more Stargate again. Stargate and Star Trek Next Generation. Those were those two shows taught me my English. Yep. Stargate even so much that at one point I was actually quite often asked if I'm Canadian. Not German, but Canadian. That was kind of nice. My answer was, I wish. So, just go on. Yeah, I'm of course, but thanks. Thank you. So, some method, and we're just going to call this, so we see, and I think, just to clean up our mess a bit, well, I don't want to delete this, because this is not source control. Let's just comment this out. And let's make a new variable. And, oh, wait, we have to include the other one first. we of course have to include our, where's my, oh, include, yeah. So where's my auto correction? Auto completion, not correction. Some class, yes, some class.h, exactly. Because we want to create an object of type useSomeClass. Again, there's always, where's my auto completion? Why does this take so long? Your English is terrible. You know, as long as we know what we want to say, as long as we know what the other one wants to. Where's my? Oh, come on. Why is the auto completion failing at me? Oh, come on. For reals? Oh, it doesn't have the U prefix. Okay, this is. Oh, wait. Genau, im Zweifel einfach auf Deutsch fragen. So ist es. So ist es. Okay, this doesn't have the. You know what? Let's grab this. The non I chose up there might have been wrong because it's new U object. Exactly. Django, you're absolutely right. This is exactly what I just. Because when I said I want to have a new class, I said none. This one up there, empty C++ class, because this sounded like it's what I want, but it's not. It's actually totally not. Show all classes. There it is. I actually want object. I actually want this one, because if I start looking for ubob, uobject, it's actually this one. Direct base class for all UE4 objects. Let's take this one. And we call this some basic. Let's try to call this some class, because basically it's a class. So create. It's only an object after we've instantiated it. Yes. Namings and terminology. Cheers. So this again takes a while, and then the file opens in the wrong editor, and then it takes a bit more whiles. No, here it is already. But this doesn't look right. Oh, yes, it does look right. Now, okay, this looks better. Now it inherits from uObject. Okay. Yeah, this explains why it didn't have the U prefix, because we've also covered this before. In Unreal, everything is prefixed by what its base type is. So everything that's coming from uObject, which is the very basics, lowest levels class an Unreal class object can inherit from, it always has the U prefix, because uObject has quite some important stuff that the engine needs. And everything. So let's do the U object. So again, now we try to make our some method again, and I'm so lazy. I always have to copy paste my class names. Some method, no parameters, and yay for clipboard history. Because having copy-pasted other stuff, I can still retrieve the UE log thing. So this is... Come on. This is some method from some class. Right. So it just prints out this message to the log, so we just can see that it worked. And of course, we have to add this to the header. And because we're neat and tidy, we properly declare this as public, even though it might be the default. But don't trust the defaults. Now it's absolutely clear. Right, and now what we can do is, if we go back in here, I think now it should work when we include some class, right? And if we go down here, we can say, ha, finally, there's my auto completion working. See, the moment you do it right, it starts working. Ain't that nice? So we declare a variable that's of type useSomeClass pointer, because this will be a pointer to an object. No, this will be a pointer to a memory location where an instance of some class, or in other words, an object of some class will be stored, and we call this some object. Great. So now we do this. Now we say new object. What? No. Oh, sorry. Some object. Some object equals, now comes the new object thing, because new object is a Unreal supplied function. It's because, again, and this is actually why I wanted to have a proper U object here. Again, I've said this so many times, some of you might that can't hear it anymore. In Unreal, we're not using any of the C++ standard primitive things. And instantiating objects is a standard primitive thing you can do in C++. So while we're in Unreal, we're not doing it. Unreal has an own instantiation method called newObject. It's templated, it's typed. So we just have to tell it of which type. And of course, we could pass parameters to our constructor, which we don't have. All right. Is there sneezing coming? Not exactly sure at the moment. So, what we have now, and to prove that we have this, I'm going to be copy pasting this from up there. A value of some object will be, we just put the some object there. And let's see what we got. I think this might be just the first thing we're going to be doing. So, stop this, compile this, and hopefully it works. But I mean, this is literally, this is like 3 lines of code. What could I possibly be done wrong? There's actually a lot of that can go wrong in 3 lines. So look at this. So we got a value of some object, which is this address somewhere in memory. So our instantiation worked. We get we have a pointer that's pointing to some memory location that has our object stored. Now we want to do something with this object. We have this some method defined in our object, and we would like to call this. Earlier on, I said, look, if we want to access what is stored at the address the pointer is pointing to, we just put the asterisk in front of it again. We make something a pointer with the asterisk, and of course, I could have written this like so as well. So I made a pointer of this variable by putting an asterisk in front of it. So I'm again putting an asterisk in front of it to be able to access this. Now, in C++, calling methods on or properties on something, on structs or objects or whatnot, you use the period, the point, the dot, or whatever you want to call it. Problem is, if I type the dot now, I'm getting quite some confusing stuff that I'm like, what? Because this period here affects this some object without the asterisk thingy. It's like it's the order in which C applies and does things, and the asterisk comes after it has tried to access something with the period. But this is no problem, because what we can do is we can just put brackets around this. So we can, like in math, with the brackets, we can force a certain order of doing things. So this is our pointer, and we're accessing what's at there, and then we just put brackets on it. So C now knows when I now do the period, I'm actually want to access the results of whatever is in the brackets. And see, here we already got our sum method that we can call, and everything is fine. And we might just try this. Yeah, I'm coming to this. Yep, I'm exactly. The arrow is exactly the next thing I want to mention. Okay, you have not reloaded my class, because this is the actual. This is what you actually do. This is what's actually happening when you're accessing an object by its pointer. But first we need to convince Unreal to actually do it. So there it is. So see, here it is. This is some method from some class. So, excuse me. So this perfectly worked. This perfectly worked. We were able to call our class. Now, computer people, and especially anyone who has a computer job that involves typing. That is, if you're a system administrator and you have type a lot in your shell, or if you're a programmer who also has to type a lot, these people tend to be very lazy. So this is a quite ugly way to type things, because you have to do asterisks, you have to do brackets, and if you forget the brackets, everything crashes and smoke comes out of your computer. All things you don't want. So there's a shorthand. There's a very neat shorthand that essentially does exactly this. Because what we can do is we can say some object, and as Dominic in the chat just said, we can do the little arrow thingy. You PHP programmers might notice this, because in PHP this is always how you access methods and properties of an object. But for a different reason, because the period was already taken for string concatenation. But that's a whole lot of a different story. Don't let. No. We are not getting off track here again. So now we can again call some method. We save the whole thing, and then we try it, and then I say one or two more sentences about it, and then we try the next best thing. See, it worked. We got 2 times. This is some method from some class, because we did call it 2 times, this time and this time. And these 2 lines, they are absolutely 100% identical. There is absolutely no difference between this and that. Depending on how low level you guys want to go with me, and trust me, I can go quite low level. If we would look at the binary code, at the assembly created by the compiler for this line and for this line, you would have no way to know which line is which, except for the order in which they appear. Because it's exactly this. This is only a shorthand for this, because the compiler knows you're lazy, you don't like to type a lot. Also, this is quite more readable than this. Let's be honest. This is way more easy to read than this. This looks super technical. This looks like you know what you're doing. You're doing super technical stuff. Unless that other people who know what you're doing know that you're not doing what you're doing, because they know if you would know what you're doing, you would know that you can use this one. Did that make any sense? I think it did. Come on, let's have some fun. So yeah, this is a shorthand. If you write it like this, if you write the version with the arrow, what happens is that this version is executed. This is a shorthand, a shortcut and also it's a bit more readable. So yeah, again, in the generated assembly, there's absolutely no difference. It's the very same as CPU commands that are executed for this. So if you want, you can use this. If you want, you can use this. It really doesn't matter. Most of the time, it's like this because it's easier and it's nicer, but you don't have to. It's totally up to you. I think nobody will think worse of you if you use this notation. So these are actually not basically. These are the very same. So now we want to pass this. Let's make. Yeah, no. I think it's okay. I think it's okay if you do a method here. This should be. Hello. Sometimes this takes a while. Do something from object. Because what we want to do now is because we need this quite often, especially in Unreal, we need this all the time. If you have an object at your location in your code, you don't always only need this at this very location. Quite often, if not pretty much almost always, you want to pass this or you want to use this at another place in your code. Like in our Game of Life example that we did, we saved all the references, all the pointers to the spawned actors. We saved them away in our 2-dimensional map. So at a later point in a different piece of code, we could access them and then do something or call methods on these objects. So we have to pass them around or store them, which is actually pretty easy. And I think most of you might not be surprised by this. So, we have our method, and methods can have parameters that we pass to it. And we just want something of useSum class. And I don't want to call it some object because then it's the same name as here, and I actually want to make clear that those names have no. Let's just call this something. I don't know. I just want these names to be different, just to make clear that this name and this name they have no relationship. They absolutely none. This is a variable that's completely separate, that lives completely on its own. And of course, this has to be a pointer. Because again, we can't pass the whole object. Also, we don't have the whole object because it can't be passed because it doesn't fit in a CPU register. So it has to be the pointer we're passing. And then we can basically already say something, some method. And of course, we add this to our header. And in this case, it really doesn't matter if it's private or public. It put it in the public block. It's perfectly fine. That is perfectly fine. It's just for demonstration purposes. So what we can do now is we can call our function do something from object, and we can pass it our some object variable. Like so. And since this is only a pointer, again, oh no, it's up here. In our some object variable, there's only the pointer to the object. And we access the pointer here to call the method. And pointers are super handy because you can pass pointers around. Because, well, they perfectly fit in a CPU register. You can throw them around. You can pass them to functions. And that's exactly what we do. We just pass the pointer to this method. That, of course, has to properly want a pointer. Because if we do it like so, it won't compile for many reasons. So we have to do it like this, because again, we are expecting this is basically a good rule of thumb. If you have anything that's not one of the primitive types like ints or bools and floats, you can be pretty sure that I am fighting with my cable again. And the other thing you can be pretty sure of is that it's supposed to be a pointer. You have to make it a pointer, or otherwise it won't work. Same goes for structs. Yep. Same goes for structs. We had already closed it again, didn't I? I knew it was a bad idea to close this up. But I've showed this. I've showed this a bit more early in the game of life thingy. Structs are also always passed as pointers. You might actually not be aware that they are passed as pointers. Okay, let me open it again. It might not look like we can do this. We can do an example. We can do an example here. I don't have to open up the game of life again. We can actually do an example here. It might not look like they are passed as a pointer. They are passed by reference, but they are. And we're doing it. You know what? Before we try this, let's immediately do, because we're running quite late. Let's do the example again. We're expecting some method from some class. We expect it to happen 3 times now, because we call it 2 times here, 1 more time here. So let's make one more. Pass by reference. All right. And we make our A again. We again make an int32A. This A is a stand-in for a struct. What I'm doing now is exactly the way it works with structs as well, but I'm too lazy to write up a complete struct now, because structs in Unreal, you also have to take care about some Unreal boilerplate stuff. A, we're running late, and B, I'm too lazy for this. It's up to you to decide which is which weighs more, which reason. Let's. Oh, you know what? Let's call this. This is supposed to be a struct, but it's not. So just pretend this would be a struct, because it works the very same way. And then we have our pass by reference. And well, this isn't int32, and let's call this some struct. But, and this again comes down to what I've said here in the very beginning, because we know this is a data structure. This is not a simple primitive type. Well, in this case it is, but just for pretension, you know. We know this has to be passed somewhere else so we can actually access the whole struct. We put the ampersand in front of that, because that means pass by reference. Actually, I can demonstrate another thing. I can demonstrate something else with this that I wanted to demonstrate anyways. So very good question there. First, let's add this to the header, and it's in the public block. That's perfectly fine, okay. And also let's assign something to it. Let's say this is supposed to be a struct equals 42. And then we call our pass by reference, and we pass it our this is supposed to be a struct variable. And of course, I mean this is this won't be much of a surprise, because it would work the very same. But it's actually for structs, this is really not such a good example. Maybe okay, let's settle on this. I'll demonstrate this with this simple int32 for now. And for next week, before we dive into whatever we're going to be diving in next week, I will prepare an example with an actual struct to properly demonstrate this. But if we, where's the blah blah? Wait, we got this print thingy here. Is there a difference between C and C++ plus structs? Not at first. Not at first. Wait. Let me try to open this because I have some structs here that I can show you. Well, you can do C-style structs in C++. That's not a that's no problem. You can no problem do C-style structs in C++ if there are really differences. If there are things, there might be things in C++ you can do with structs you can't do with C, but I have to admit I'm currently not aware of them. It's loading, and maybe eventually it will be done loading. It's still loading. Because I can show you some of the structs I did, and those are actual structs that are used. Like when I hit the play button here, many of the things that are then happening in the play field actually use them structs. It just has to finish loading. So, where are some? Let me see. Economy system, no. Inhabitants, trader, types. Types, I usually store my structs in types. Yeah, look at that. Oh, this is a very simple one, trader stats. This is a very, very simple struct. Yeah, so basically, no surprise there. Type name, type name, type name. You can, I'm not sure if you can do this. Oh, there's one thing I'm not sure if you can do this in C. And I actually don't like that you can do it in C++. I don't like that you can do this at all. You can actually put methods in your structs. You can do that. You can put methods in your structs the same way you put methods in your classes. And I don't like this. Why don't I like this? Because where's the difference between a struct and a class? It's like using static classes, and who does this? Whoever uses static classes or static methods is immediately fired. So when you define type struct, then you can use it as a return value without pointer. I'd have to try this. I'd actually have to try this. In C, you can only use function pointers in structs. Yeah, in C++, you can actually put methods in there. It's horrible. I don't like it. Unreal does this a lot. Because why not make a proper object out of it? That would make quite more sense. I'd actually have to try this. Gonna admit I'm not exactly sure. I'd have to, but I think internally it's passed as a pointer anyways, because it can't be any different, because it has to fit. I'm gonna be playing around with this. I'm gonna be trying this out, and we're gonna be talking about this next week, and maybe we can answer some of those questions. Because how would it pass a whole data structure as a return value? Technically, it can't. Unless the compiler does some magic and deals with the pointers internally without you noticing. That might be the case. I'll be trying this out. Yes, always on Thursday. Let me copy this quickly to somewhere over the rainbow where I don't forget this, because I'm definitely noting this down for next week, and we're going to be talking about this next week again. Yes, it's next week again, Thursday, 6 p.m. CET, usually till 9, which we're a bit over now, but, well, stuff happens, right? It happens. So, where were we? We were here. No, yes. Wait, Possible. Oh yeah. Okay. Okay. Actually, wait. This is kind of sad. Why does rainbow brackets not work on Rider for Unreal? Why does rainbow brackets not work here? Because I really miss my rainbow brackets because I always get confused with the brackets. So this is supposed to be some struct. I mean, there's... And just drop the format. Well, this will be absolutely no surprise what happens here, because of course we're printing out, and for some reason the argument does not match any printf form. Oh yeah, because I forgot the % sign in front of that. See, this is why we're using IDEs, and why we should always take note of, like, I mean, okay, this green squiggly line tells me it can be static, and trust me, no, it can't, because if I use statics, I have to fire myself. So I don't use statics. Yeah, it's of absolutely no surprise that when we print out the value of this, that we actually get the 42, because we put it in here. This ampersand right now has absolutely made no practical difference up to here. But there's one thing. This is what I was talking about at the very beginning when we were talking about the ampersand thingies. Because if now I say sum struct equals 1337, and down here, after we called this function, we will output this. What do you think we're getting? I think most of you will know anyways. So let's try this out. First the stop, then the bar cube, and then let's see if everything works. Compiling. Bum 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 bum, and done. And of course we have to compile it. This is an Unreal's reload and hot reload. This doesn't work since ages. So now it did. Look at that. Here's the magnification. So look at that. We have, like expected, our 3 calls from some method from some class. Wonderful. Then inside our pass by reference, we of course get the 42. No surprise there. But back in our original piece of code, jeez. Back in our original piece of code, which if I open the right window, then we'd actually see it. See, first we call the pass by reference. And after the pass by reference is done, we print out this is supposed to be a struct value. But yet, and inside the pass by reference, we set the sum struct, which is basically only the parameter we're giving in. We assign it the 1337. But yet, when we print out our this is supposed to be a struct, we also get the 1337. And this is exactly what I was talking about earlier, when, since this parameter is defined with the ampersand, usually when you have, like in this case, when you have a parameter, the compiler takes care that for the scope of your function, like any other variable you define in your function, You also get memory reserved somewhere for this variable, so this pointer can be stored into this variable. You can eventually access it and do nice things with it. However, this is a variable only available to the scope of your method, so whatever you do inside your method stays in your method. You can change this something, you can change this variable to whatever you want. No difference. Like if we remove this ampersand, since this is just an integer, this should actually work. If we remove this, then oh yeah, of course it no, wait, why of course it fails? Illegal call of non-static, what? Or a member function not found in what? Okay, maybe I forgot to remove something else. This is just an int and oh, okay, yeah, of course I have to, of course. If you change it in a CPP file, we have to change it in the header file as well, right? Yeah, classic. You have to change it in the header as well if you change the definition of your function in the CPP file. Classic beginner mistake. Yeah, I haven't done C for quite a while when I started Unreal Engine again. So look at that. Look at this. Sum struct is 42. This is the value inside our pass by reference function. And then we get that this is supposed to be a struct, which is after we call the pass by reference function, and there is still the 42 in there just because I removed the ampersand. Because, and this is what I explained at the beginning, let me put the ampersands back everywhere. So, because when, let's put it there. Because when you define a parameter for your function with the ampersand, the compiler will not reserve you memory inside of the memory block for your function where this variable is stored in. Instead, you will be able to use this as your own variable in the scope of your function. But instead of getting a new block of memory where the value of this variable can be stored, the compiler takes care that when you access this variable, it's actually using the memory from whatever variable it's called with. And since we called our pass by reference function with our this is supposed to be a struct variable, which is this one up here that has an address, we could actually we could actually here. So address of some struct, and we just make this a neat little pointer, and this is our supposed to be, and you say cannot print value of int, because like so, right? See, because we want the address, because this is just an integer value and we want the address of it, put the ampersand. We know this by now. We also can do this here, only that here it's called some struct, like so. Okay, this is the address of this is supposed to be a struct, and we get the address of this variable. Then we call the pass by reference, and it tells us the address of its some struct variable. Then we print it out, then we change it, and everything's cool. All right, compile and run. Boom, 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 boom. It always takes a bit longer when you change something in the headers, because Unreal then has to additionally run the header utility over everything, and that takes a bit more time. So, do I have the, yes, there's the addresses, right? So, look at that. We got our address of this is supposed to be a struct, which is blah, 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 blah. Let's just take a look at the last four numbers, which is 8548. And then we got the address of some struct, which is the parameter that we passed into the pass by reference function. So it's valid in the scope of that, but it is 5848. And also here, 5848. So the addresses of these two variables, they look like they are different variables. And they are even in different functions. But the memory addresses that are accessed to store values in and to get values out are the very same. And this is because we put the ampersand in front of the parameter definition. So the compiler doesn't reserve a new memory space. It just uses the address of the variable it's been called with and just uses this one to access the values when you access the variable. And this is why when we, inside of the pass by reference function, when we change the sum struct variable, we also have the changed value in our this is supposed to be a struct variable. Not really intuitive, but if you think about it a few times, it slowly starts to make sense. And this is used for several reasons. This is used to pass objects or data structure. Well, for objects, you sometimes you actually say, "Come on, just give me the goddamn pointer. I don't want anything else." But this can be used to just say, "Yeah, I want a structure, but yeah, give me the address because you can't put the whole structure in the CPU register." Because look at where we call this. This ampersand here, you can ignore this. This is shown by my IDE because my IDE is the message up here. Let me just copy paste this block into a text editor, and you will see there is no ampersand here. I hope you can see this. There is no ampersand here. There's just pass by reference and then my variable name. There's nothing special. There's no asterisks. There's no ampersands. There's nothing. I passed. There's absolutely no difference in this call as when it would not be passed by reference and as would it normally like we're used to. The fact that it's shown here as just my IDE, letting me know that, dude, be careful. This is passed by reference, not by value. But if we just copy paste this out, you can see this call has absolutely no difference to the usual calls that we are used to. So this makes it a bit more easy for who's calling your method, because you just slap your variable in, everything's passed, and the fact that this is only passed with its address and not its actual value is taken care of by the method that's being called, and that has to take care about all the nitty-gritty and stuffity stuff. So I hope this is somewhat clear so far. Again, as said so many times already, if not, just let me know in the chat, on Twitter, in the comments of the YouTube upload of this later on. Just let me know. So there's one last thing I want to show you to make the confusion complete. There's one last example I want to show you. Basically, we've talked about this already. So if you followed all the things we've talked about, it should make a bit sense. And this is only a demonstration of the things we talked about, because like when we in the game of life, when we spawned our actors, we got back a reference to the actor because well, we didn't instantiate it. The function instantiated the object and took care of everything, and then just got us back the pointer, the reference. So what if we want to do this? So let me scrap all of this. I don't think we need this at the, yeah, let's just scrap this. So let's say we have another function, and again I need to copy paste the class name here. So let's say for whatever reason we have a different method that even can be in a different object, but this method will create us the object and will give us back a reference to the object, and we will then call the object. So let's call this make object, and I leave the parameter up there empty for now. And yes, of course, we have to clean up the header, which I can do is delete those already, so we only have to add this one once we're ready. So what we want is we have our SumObject class, and eventually we want, just like we did before, we want to call some method from our class. But for whatever reason, for some arbitrary reason, we are not able to directly instantiate this object here in our code to just call this method. We need another method that creates us the object and then gives us the reference or the pointer to the object back, so we can then access it. So what we'll be doing here is basically we say new object. Oh no, this is, let's call this the object. The object equals new object, and this is our useSum class, and that's basically it. So this can already be the parameter, because we can immediately, since in this case we only want to create the new object, we can directly assign it to the parameter. So of course we have to start with something like some class and the object, because this is just our variable. This is just the parameter, the variable with which we can access the parameter. And of course this has to be of type useSum class, because this is what we want to create and this is what we want to give back. So because this is an object and we had this rule of thumb, everything that's not a super primitive type is always being passed back as a pointer. Did you hear something? Did something fall down? Is this my cable again? Thought I heard a weird sound. Anyways, I think it was the cable that fell down. So this by now should be obvious that this has to be a pointer. But we want to pass this back to whoever called us. And remember, we just did this. We just did this with our pass by reference method. We had a variable as parameter, and we could write into this variable, and this whatever we've written in there was then available up here, because we didn't get a new variable, we got the address of the other one. And what we did was we did put the asterisk in front of our variable name to make clear, look, I don't want a copy of the value. I just want I want to use the very same memory location as whoever calls me uses for this value. I hope this makes sense. This should make sense by now to you, because we've talked about this for so long now. And if it doesn't make sense, then I've talked not good enough about it. So please do ask. But this is because since we're having an object, we only can deal with the pointer of it, not with the whole object. And since we want to write into whatever variable we are called with, we're putting the ampersand in front, just before, like we did with the pass by reference, only that it was just a simple integer that we changed. Now we want to change the content of this. So we put the ampersand in front of that, which then results in, if I write it like this, it looks a bit more techy, like you totally know what you're doing. Which results in stuff like this. You have some class, you have the asterisk, and you have the ampersand, and then you have your object. But what should happen now is, if we call the make object, if I manage to make object, there it is. If we call the make object and we give it our sum object variable, because of the ampersand, this variable and this variable point to the very same memory location. So whenever I change the memory location from here, since I'm accessing the very same memory location from here, I'm getting the very same result. So if I write a new object into this variable, I'm also getting it here. I say this, and I know this might sound nonsense, but I hope this makes sense for you. So yeah, and this results in fancy things like that. But if you think about it, and if we write it like this, it makes a lot more sense. Because then you know, okay, yeah, this is a pointer, and this is only passed by reference. Both of these things we know by now, and we know how they work, only that now we use them together, combined. So it should work that when we compile this now, we should get this is some method from some class, because, okay, we're defining the variable up here. We're calling the make object, which puts us a reference to an instantiated, ready-to-use object into our sum object variable, so we can access it. Would the code compile without the ampersand, and if so, what would happen? We try this, but at first I try to, let's see, if we do not put the ampersand there, yeah, of course we have to change it in the header as well. It will crash eventually. It will definitely crash. Yeah, my IDE already tells me. It will compile. It will absolutely compile, and it will crash right here. Because what now happens is, and I'm thinking about, you know what, we could actually, yeah, let's run this in debug mode so we can actually see where it crashed. So let me stop this, and let me close this, and let me close this, because I don't think we need them anymore today. So what now happens is, now this is not passed by reference, this is passed by value, which means when I make this call, whatever is the contents of this variable, which at the moment is undefined because we haven't put anything there, and this is a very, very dangerous thing in C++ or in C, and we've also talked about this before a bit. Variables with as long as you haven't explicitly written something into your variable, and you have for as long as you have assigned it a value, this variable is undefined. You have no idea what's in there, because C or C++, they do not initialize your variables with a default value. In other languages like C# or PHP or whatnot, it always initializes new variables. So if you define a new variable, it will always be defined with a default value for this type of variable. Like integers are always a 0. pointers will always be, well, okay, there's no pointers in many other high-level languages, but objects. If you define a variable this that's supposed to be of object whatever, there will be a null point. There will be null in there. So it will always be initialized with a proper default value matching for this type. This is not the case in C. In C, in a way, you get a random value in here, because, as I stated before, the compiler reserves you some memory. The compiler says, okay, you have a variable, you want to store something in there, and I reserve you this memory area where you can store your value. It might be that there is still data from another program that ran hours ago, or maybe even only seconds ago. But this memory location the compiler reserves you for this variable might have been used before your program ran. So the actual value of this variable at this point is whatever is in memory in this location from whatever happened before on the computer. That means you have absolutely no way of knowing what it is. You might be lucky it's 0, which will crash anyways, because null pointers, you can't dereference them. Or it might be some random junk. And it might have the weirdest effects. And I actually had this problem with the Game of Life on our second evening when we did this, because I forgot to initialize one of the 3 world locations. It was uninitialized. It was undefined. And the things spawned way beyond what Unreal Engine is able to handle until I intentionally set it to 0. So this is undefined. There's some random junk in there. We can actually see what random junk is in there by putting a breakpoint there, because we are running this in debug mode, so we can put a neat and nifty breakpoint. So breakpoint means the program, when it executes, will stop, will jump into, it will stop right at this line, will jump back into our IDE, and we can actually look what's in this variable. And then we make another breakpoint here, because then we're going to be looking what's inside of this variable. So what happens without, to get this question finally answered, what happens without the ampersand? The value of this variable will be copied into this variable, and this variable will be at an own location in memory. We will be instantiating our object into this variable, and that's it. Then this method is over and execution continues back down here. But since this variable was its very own, with an own memory location, this variable has never been changed. It still has its original undefined value. And then we try to call a method from this undefined memory location. And this will crash. This will absolutely... So, long story short, it will compile fine, and then it will crash right here for the reasons I just stated. And we're going to try this. This is development, let's say debug game editor Win64, and go. So this might take a while, because it first has to compile everything in debug mode. And since it hasn't done this before, this might take a while. But while it compiles, I can already tell you, when we put the ampersand back, it even doesn't compile me. It even doesn't compile it, because it noted here, uninitialized local variable. Oh, this is a clever compiler. Look at it. It does not compile, because our compiler is a bit more clever than I expected. Look at this. Pointer this is this one. Look at this. Uninitialized local variable some object used. And does he tell me where? Oh yes, of course, line 64. This is this one. So he already knows this is a pointer variable, but there has never been something sensible written in this. So we can fix this. But then these breakpoints don't make much sense. We can fix this by initializing it with a null pointer. It will still crash. It will still crash when it comes down to here. But I think it should compile now. Interesting. The compiler knew that we had a pointer that we never initialized with a proper value. I didn't expect that. See, this is good while we try these things. And I think eventually, oh yeah, there it comes. Unreal is loading. Bum, 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 bum. All right, you know what? Let's actually put a breakpoint down there, so we can peek into, you know what? Let's say the object equals the object. I just need a line to put a breakpoint. Wait, what is this? Is never used. Oh yeah, okay, this is okay. I just need a line where I can put a breakpoint. So because the line with the breakpoint is not executed. It breaks at that point before the line is executed, so I need a breakpoint after this line. But still, while we are inside of this method. So let's run this. Okay, now, okay, I've just executed this. I've just launched this. And this is the breakpoint. So we are actually currently inside the running program, and we can peek into those variables, what's in there. And there is a pointer to a U object. Let me magnify this for you a bit. See, there's a pointer to a U object, and this is the address. This is the actual contents of the variable. It's of type uSum class pointer, and this is the pointer. This is the memory location of the object that was just instantiated, which kind of is expected. Now we continue execution. And where we are. Is it still living? It should have crashed. Or maybe it knew that it's a null pointer and it ignores null pointers and it just doesn't call something. Maybe it's again a bit more intelligent than I expected. Let's put a breakpoint here. Maybe it's a bit more clever than expected because it knows there's a null pointer in here. Hello? Can I? Oh yeah, there it is. Okay. Execute this again. So we're in this function. The object has been created, and you can see here is as well the object, and there's this address, there's this pointer. Everything's cool. Then we step ahead, and we are at this point, and here's our sum object variable. And our sum object variable currently is null. And I think it's, for some reason, it's clever enough to know that it usually, it should crash. I'm not exactly sure why this works. It totally should crash because there is such a thing as a null pointer exception, which usually happens when you try to access something from a pointer that is literally null. But for some reason, it's clever enough to not crash here. But as you just saw, this thing, no, other way around. This one has a different value to this one once the execution is complete. So now let's stop this. Let's put the ampersand back. And let's, oh yeah, and of course we need to change it in the header. And let's try this again. And hopefully the hot reload now works. Just to make sure, I'm going to be compiling it 2 times because since like I think 4.17 or something, they have horrible problems with the hot reload stuff. So play this level. So again, Here we have our the object, which is the variable in our make object method, which has FC10 as the last four digits of its contents, and we skip ahead. And now we look here. Some object now also has FC10. Now our sum object variable has the very same contents than the new object variable had before, even though we initialized it with a null pointer. And look at that. Here's even the address where some object is. It's the contents actually. It's the contents. Nice. Because of the ampersand, all this stuff I explained before. This variable accesses the very same memory location as this one. So it's like, yeah, two things pointing to the same thing. And this is why when we write something into this one, it also goes into this one. Explained this a lot previously. So now this should work. And if we go into the editor, and there is it. This is some method from some class, only that we created the object in a completely different method. We created the object down here in this method, passed it back using this by reference parameter that by coincidence is a pointer. If it's not a pointer, it's not so confusing, but it's a pointer, and this might become, it looks weird because of, oh boy, now we have both of these pointer thingies there. This looks like, oh my god, I will never be able to understand this. But if you put them apart and you actually see, okay, this is just the pointer, this could also be just the int32, and then this would be no problem. Or the other way around, this can be a pointer, but this is like so, also no problem. If you understood both separately, then all of a sudden this construct, it looks so weird and it looks so complicated. And it is a bit complicated to understand at first, but if you've understood the separate things, like this is a pointer and y, and this is also a pointer, this is by reference, and why and how, it all of a sudden starts to make sense. And it's not that much voodoo anymore, but it's definitely something to show off at the next party. Like, look at that, I can do pointers at pointers. I can have things pointing to things pointing to things. Trust me, nobody will bother you for the rest of the party of this evening. So yeah, this was the last thing I wanted to show today. Was there anything else? Yeah, well, okay, there's a bit of tinkering with strings I had originally planned, but we kind of did this already last week actually, when we added this one, where we just added something to the pointer. So I think I made this clear. This should be perfectly fine, and well, I hope I demystified this construct a bit. Especially if you write it like this. Remember, the white space doesn't matter. It doesn't. You can write it like this. You can write it like this. You can write. Oops. You can write it like hello. You can write it like this. It doesn't matter. It's the white space really doesn't matter. If you write it like this, or this, or this. It looks like voodoo rocket science. Written like this, it's already a bit more clear, but you guys now should exactly know what's happening there, why this is happening, why this is working, and how this is working. If any of this is unclear, and there is still questions and confusion, or like, I still haven't gotten my head wrapped around that, please let me know. There's so many ways use the hashtag, use the Twitter handles, use the comments on the videos, send smoke signals. I don't know, whatever. I'd be more than happy to answer any more questions you have with this. I will look into the structure thing. If we can, maybe we can just pass structures around instead of using pointers. But then I would have to find out why. I think because the compiler actually internally might convert everything into pointers, like with this one. I mean, look at this. We just call this, and just by looking at this line, you have no idea that this is passed by reference. You can't. There's no way to determine it just by this line alone. You have to look here. So maybe this is also some of the magic that goes on when using structs. But I will be trying this out and make up an example. And then, maybe we can actually do this with structs. Then it would be interesting to find out how this works internally. Maybe we actually, I think starting Ghidra and doing reverse engineering of the compiled code would go a bit too far, wouldn't it? I think this would go beyond the scope of this tutorial. Reverse engineering the compiled code and see what what CPU commands the compiler actually made out of it. Yeah, I think this would go too far. But let me know if you want to see it. We won't do it here. We will just do it at some other place. But if you'd be interested in doing some reverse engineering of binary code back to C, let me know. Because I haven't done that for quite a while. I haven't done this for, let me see. Wow, for over 20 years. The PSP was 2004, 5, 6, 7, 8, right? So I haven't done this for about 20 years. So don't expect miracles. I might horribly fail when trying this now because I haven't done this for so long. But to be quite frankly, I think I'd like to. Let's do this. Let's do this on the other. Let's do this on my channel someday. We should totally do this. This is fun. But we're not doing this with Unreal C++. We're just doing GCC on the command line because all the overhead and the boilerplate stuff. You followed me on my channel. I'm very glad to hear this. Thank you. On my channel, it's a mix. Sometimes I do development stuff. Mostly working on my own projects. Like I need to add channel points for this back there. This is actually something, this is pretty neat. And I need to add channel points. At the moment it only works using the chat. Like when you say, I don't know, when you do it like so. Oh, of course. Yeah, this is in German. If I do it like so, this works. See? This currently only works via chat, and I want to change this so it's actually using channel points. Let's put this back to a color that fits. Why doesn't this work? I didn't put anything. Yeah, you actually have to because this is supposed to be for you have to use the German names like Grün. I can't put the English ones in because this is supposed for the people in my channel to be used, and they are mostly German speaking. There is a kind of lila. Try Twitch as color. Try the Licht command with Twitch as color, and you might get the purple lila thingy. And that's my cable falling down again. See? And Twitch color. Yeah, the color names are currently in German only because this is pretty much supposed for the people on my channel, and they pretty much yeah, they mostly speak German. But it's no problem. It's a simple mapping. It's an array of that maps names to light themes. It's very easy to add the English color names as well. But I want to change it to channel points anyways. I want to change this so the channel points can be used to switch the light, because I think that's way more funny than just using the code, the chat. Because come on, what else would you do with channel points? There's basically nothing you can do with them. Yeah. So, and I was just mentioning this because sometimes I do development stuff on my channel, like changing this thing to channel points. This will be one of the things I will be doing on my channel quite soon. Sometimes I just play games. Sometimes I just sit there and chat with you guys or with whoever's there. Depends. Sometimes this, sometimes that. A good mix of everything. So yeah, thank you for the follow. And I think this finally concludes with 1 hour of overtime. This concludes tonight's session of Coding for Unreal Engine in C++, Episode 7, Pointers, Part 2. Yeah, I think we made it. I hope that I could shed some light into the mysterious life of pointers. I think we've covered quite some neat things, especially stuff like this. Yeah, demystifying this a bit. So the next time, Dominic said something about that where you saw that. Wait, then once you know before you put the asterisk ampersand, I see before, but you've never known what it goes. Good explanation. Okay, cool. Thanks. Yeah, again, yes. So, do I do Unreal Engine? Do I do Unreal Engine on my channel too? Yes, because the project, our main project from work, we want to do very openly, and we want to show many of the development. So sometimes I even work on this a bit. I've shown this yesterday. For the guys of you who've been here yesterday, might have already seen this. This is the current state of our project we're doing at work. You can build some cities here. The UI gets in the way sometimes, and you can put some cities here, and you can put some cities there, and you can put roads. Eventually, this is supposed to become a full game that hopefully will be a lot of fun. But there's still a long way to go, and I work on this on my channel quite a lot as well, because we actually want to do. Why can't I put my boats there? Anyways, because we want to be quite open with the development. We want to get feedback quite early. So I openly work on this on my channel as well. So yes, Unreal Engine, sometimes maybe even Unity, depends on what I'm currently working on. All this sort of stuff. Absolutely. Yep. Can do. Will do. Does do. All right, guys. Well, let me, with the nice Twitch color, come back on the big screen for a second. Guys, thanks for being here tonight. Let me just see. I'm going to be finding the right button. We'll check it out. Thank you. Very much appreciated. Yeah. Thanks for being here tonight with me. Thanks for asking all the questions in the chat. Thanks for having a wonderful time. I had a great time again tonight, and I hope you had as well. And we could demystify all this pointer stuff a bit. So in the future, when we're doing some more C++ code in Unreal Engine, we're trying to do things and try to see how things work and how things are done. And when we are pointering around, you will sit there and say, yeah, I know exactly what that does. All right, guys, thanks again for being here. It was a wonderful evening. Hope to see you again. Next week, I will be taking over this channel again 2 times. For the last time, 2 times. Because next week is the last week where the game dev show that's usually on Wednesday is still on vacation. So next week on Wednesday, I will be sitting here and basically just talking and chatting with you about all things game dev. We don't have a definite topic. There's nothing special we talk about. I just have Unreal open in the background, click around a bit, show you stuff maybe. Yesterday, yesterday I actually made nothing because we just kept chatting and chatting until the night was over, which was wonderful. So yeah, next week, Wednesday, we can meet here at 7 p.m. Central European Summertime and just have a general chat about all things game dev, and I will be having Unreal open in the background, and so the screen is not so empty and boring. I will be having something moving on screen while we chat. And next week on Thursday, we continue with this series with C++ for Unreal Engine. And let's see what nice things we're going to be looking at next week. How to do them in Unreal now that we can properly point at them. Yeah, that sounds good. Alrighty, so without further ado, I wish you a wonderful night, or I don't know, depending on your time zone, if you're watching the video, whatever you do, wonderful rest of the day. Thanks for being here, thanks for watching, and yeah, see you around. Bye.